I'm here to tell you about a special sustainable challenge we're doing together at SDI. My name is Tanisha Kapoor. I'm living out when I was a young student like you that wondered what can an ordinary girl like me do about a big problem like climate change. So from my dorm room, I started an app and a movement for climate action called Cooling Retrofit. Living here. Today, we have users in 150 countries taking climate action on the app. We've reached over 25 million people. And when I first started out, I couldn't have believed that this came from us. So trust me when I say this, the innovations you brought at SDI had massive potential. So I've come to meet all of you. You're going to be seeing me very soon. And I've come bearing a special gift. On Cool the Globe app, we're hosting a special challenge just for you while you're here at SDI. So all you have to do is download Cool the Globe app, join the SDI community. You can come and calculate your event footprint on the app and then start taking actions to reduce it. You'll see simple sustainable actions you can take while you're here at the campus, and we have a live free report that will be tracking the participants taking the most amount of climate action. The top 10 participants to win this challenge will be named as Climate Champions of SDI 2026. I can see that you've come here with big dreams, big innovations, and inspire me. We believe that the first step to changing the world is changing yourself. So through this step, we want to recognize the participants who are truly ready. We're also tracking in real time the collective emissions gains by so download Cool the Globe app, record your first climate, join the SDI challenge, and I'll see you on the other side very soon. Let's make this a truly sustainable event together.
Good morning, everyone. We are supposed to start at 10 sharp, so that's when we'll officially start. But welcome to the finals, and good luck to all the teams and crew members. You have a much longer day than students. Good morning, everyone. Jury members, everybody present here in the room today, and those of us joining online. Welcome to the Residential Cooling Retrofit Divisional presentation for SDI Finals 2026. RCR, the Residential Cooling Retrofit Division, it tackles a pressing issue in our warming climate, which is efficient cooling for homes that make up 80% of existing buildings in India. This division is all about product innovation. Teams have designed, built, and tested prototypes to enhance cooling while ensuring that their solutions are easy to install and appealing to users. I'm excited to welcome you all to the presentations in the RCR division and to see how these students are making cooling more accessible and sustainable. My name is Amritraj Aman, and I am the MC for the day. And it's my job to keep all of you on time. And I'm going to take this very seriously. And this goes both to the teams and the jury members here. Our finalist teams have put up a lot of hard work. They have submitted their project reports approximately 1 month ago. And today they will present their work to the jury. Teams, you will have 20 minutes for your presentation, followed by a 10-minute Q&A with the jury. There will be a 5-minute break after the team presents, and you must use these 5 minutes to move your prototype out of the room and for the next team to move their prototype into the room. The Residential Cooling Retrofit Division has 3 jury members who have expertise in product development, entrepreneurship, and cooling. We have Kshitij Sawant here, solution consultant at Sehat Software. Hi, Kshitij. Next, we have Swati, who's a director of Terra Redis. Swati, good morning. And our third jury member is Yash Sangvi, head of IoT practice at Atomberg Technologies. Hi, Yash. A very warm welcome to you here to the presentations. So the jury members have had 3 weeks to review the reports that were submitted by the teams. They have looked at your work in detail and have already assessed your entries for the 10 contests in the decathlon. Teams, your presentations here today will help them to hear your narrative. They will assess your presentation and they will assess your mastery over the solution through the Q&A sessions, and they may revise their scores on what they hear today. Jury members, I'm excited to have you meet the teams today. I will need to interrupt people to ensure that we are on time, and that includes you, the jury members. I hope you don't mind too much. Please keep your comments and questions short and to the point. Okay? All right, are we ready to begin? Right, so let's start with the presentations. The first presentation is by Team Numa. Their product is named Sync. So it's a sensor-driven smart retrofit for Windows that syncs with existing fans and ACs. Team Numa, could you please take the stage? Next back, there's no laser. Get your charger, quick, quick. You have 2 mics. Wait and point it if you want. That's absolutely fine. Stop it.
Okay, come on, guys.
Actually, and then come. इस तरफ से आओ, इस तरफ से आओ.
All right, Team Numa. So this is your instructions for you. You'll have 20 minutes to present your presentation to the jury, followed by a 10-minute Q&A. Okay. At 15th minute, I'll ring a bell, a single bell, to announce that you have 5 minutes left. And at the end of 20 minutes, if you have not stopped your presentation, I'll not stop ringing my bell. So you will not have a 21st minute. Okay. And you have the timer to keep you on track. Okay.
Sure.
Right. Uh, yeah. Team Numa, your time starts now.
Good morning, respected jury members. We are Team Numa and we are representing Manipal School of Architecture and Planning and Manipal Institute of Technology. Our team brings together a multidisciplinary. Our team consists of 8 architects, 1 product designer, an engineer, and 2 sustainable designer. And together we are proud to compete in residential cooling retrofit and compete in the Solar Decathlon India 2026. Today we are excited to present Sync, a smart retrofit Windows module engineered specifically to conquer the unique thermal challenges of warm and humid climate. Before we dive into the technology, let's ground ourselves in the environment that drove our design. Our project is rooted in the coastal regions of Karnataka, which is Udupi, and where the average temperature is 27 degrees Celsius and average rainfall is around 4,000 millimeters, and the humidity is relentless. In climates like Udupi, thermometer only tells half the story. The real villain is the humidity. High airborne moisture prevents sweat from evaporating, trapping heat against the skin, leaving residents feeling sticky and uncomfortable. We realized quickly that simply lowering the temperature wasn't enough. We had to address the moisture. So, what exactly and who exactly is Sync built for? Udupi is a growing district with a strong economy and over 3.2 lakh households. Our analysis identified the bedroom as the most critical space for intervention, and hence we tried to make it uh, comfortable and provide quality sleep for the residents. We focused our efforts on middle economy income families, and a demographic constantly forced the weight their personal comfort against the dread of rising electricity bills.
While most participants relied on fans and air conditioners, many still experienced dampness, condensation, and that sticky feeling. Most importantly, every respondent expressed willingness to try a retrofit if they could see it demonstrated first. We also identified an acceptable price range of 5,000 to 10,000 rupees, which helped shape our market understanding. With the problem clearly defined, the next question was what kind of solution could actually address it? Our ideation process explored 10 different concepts. Each was evaluated against user desirability, innovation, engineering feasibility, sustainability, and commercialization potential. Several concepts were eliminated because they focused only on temperature, consumed excessive energy, or were difficult to retrofit into existing homes. Among all the concepts, Sync emerged as the strongest performer, offering the best balance between user needs, practicality, and scalability.
So now a question naturally arises, what exactly is Sync? So Sync is a smart window-mounted retrofit system that synchronizes existing fans, air conditioners, and ventilation pathways using real-time temperatures and humidity data. Rather than replacing existing infrastructure, it enhances what homemade homeowners already have. The system consumes only 20 to 25 watts of power, introduces filtered fresh air, reduces indoor humidity by some extent, and operates through 5 intelligent modes specifically tailored for warm, humid climates. Why is this different from conventional cooling? Because most existing systems solve either temperature, ventilation, or humidity, but rarely all the three together. As a result, occupants continue dealing with stale air, moisture related discomfort, and increasing energy consumption. Sync bridges this gap through adaptive comfort optimization, humidity aware ventilation, intelligent device coordination, and controlled fresh air intake. Equally important was making the system simple to use. The design philosophy behind Sync is centered on simplicity, adaptability, and accessibility. Users can easily view temperature, humidity levels, and operating modes in real time, allowing them to understand what the system is doing without needing any technical expertise.
So, how does sync work? At the heart of sync is an adaptive comfort based control strategy designed specifically for warm and humid climates. The system continuously monitors indoor and outdoor temperature and humidity through environmental sensors. Rather than responding to temperature alone, sync evaluates the total thermal condition of the space using psychrometric relationships and enthalpy comparisons. Based on these conditions, sync determines the most efficient pathway to comfort and coordinates three devices simultaneously: the air conditioner, the ceiling fan, and the window blower. The controller always prioritizes the lowest energy strategy first. If outdoor conditions are favorable, ventilation and air movement are used before mechanical cooling is introduced. A key principle behind this approach is elevated airspeed. By increasing air movement around participants, sync enhances convective and evaporative heat loss from the body, allowing occupants to feel comfortable even at higher indoor temperatures. In other words, sync doesn't simply cool the room, it improves how occupants experience the space. As we are dealing with residential bedrooms, our main focus is good quality sleep. Occupants having to change the modes manually goes against the very notion of it. Hence, sync automates the entire process while you catch up on a good night's sleep. To achieve this, sync operates through 5 intelligent modes selected using enthalpy based decision making. Let's take outdoor conditions at 25 degrees Celsius and 50% RH, and indoor conditions at 30 degrees Celsius and 70% RH. When outdoor air contains less total heat than indoor air, the system enters ventilation mode, introducing filtered fresh air and removing accumulated indoor heat. When conditions fall within the adaptive comfort range, say indoors is about 25 degrees Celsius and 70% RH, sync transitions into hybrid adaptive mode. In this mode, the ceiling fan and window blower work together to increase airspeed around occupants, improving perceived comfort while consuming very little energy as compared to mechanical cooling. As thermal stress increases, the system enters AC assist mode. Here, sync coordinates the air conditioner, fan, and the window blower together, ensuring that cooling is delivered efficiently while reducing compressor runtime compared to conventional AC approach. Nighttime purge mode takes advantage of cooler nighttime conditions to flush accumulated heat from the room and prepare it for occupancy. Finally, isolation mode protects indoor comfort whenever outdoor conditions become excessively warm or humid. The key idea is that mechanical cooling becomes the last option, not the first.
As we can see, we are right now simulating the night purge mode. Like just before the night purge mode, the exhaust part is on, and after a while, the lower blower part would be blowing in the cool air from outside. Now let's talk about the prototyping slide. Of course, a concept is only meaningful if it can be validated. To test our ideas, we developed physical prototypes. Our first prototype focused on airflow enhancement. As you can see, we used 2 axial fans and filtering components in the behind. So what we did before was we had two axial fans for the inlet of the air, and we had one inlet on the bottom to minimize the air filter use and ease of cleaning the filter. But later we realized that that much area of air inlet is not enough for the whole room. So that is there, and also axial fans are noisy and they don't have enough CFM. So what we did in the second prototype was change the two axial fans to one tangential blower, which equally and homogeneously spreads all the air inside the room. It's not focused into one area. And the axial fan still stands there because the exhaust needs to be direct and it should be more powerful than the inlet. So that's the prototyping part. Yeah. So that's what we did. And after the first prototype, what we did was try to improve the seal of the window. So to keep the window locked even when the prototype is in there, what we have to do, we just have to unscrew the lock which is on the window frame, then screw it in the product part on that side, which will lock the prototype, lock the window, sorry. And as you can see, I spoke about the optimized airflow. And yeah, that is the prototyping part.
So we'll move on to the technical testing. With the control strategy established, the next step was evaluating the performance. To assess the effectiveness of sync, we conducted simulations under warm and humid operating conditions and tested multiple cooling scenarios corresponding to different operating modes. Our objective was not simply to reduce indoor temperature, but to determine whether adaptive comfort strategies could improve comfort while reducing energy demand. We evaluated multiple performance indicators, including indoor temperature, relative humidity, air changes per hour, cooling energy consumption, and degree discomfort hours. This allowed us to assess both comfort, performance, and energy implications across different operating conditions. The simulations clearly demonstrated improvements in both thermal comfort and energy performance. Under baseline conditions, indoor temperature reached approximately 31.5 degrees Celsius with relative humidity around 70%, resulting in approximately 11 hours of degree discomfort. Under sync operation, indoor temperature reduced to 26.8 degrees Celsius while discomfort hours reduced to only 4 hours. Although the reduction in relative humidity was relatively modest, the combination of increased air movement, fresh air ventilation, and intelligent cooling coordination significantly improved overall comfort conditions. Most importantly, cooling energy consumption reduced from approximately 1.8 kilowatt hours to only 0.32 kilowatt hours. This corresponds to nearly 80% lower cooling energy use while simultaneously improving thermal comfort. An important observation from our analysis was that comfort improvements were not driven solely by temperature reduction. Thermal comfort depends on multiple factors, and along with the environmental conditions, the body's ability to dissipate heat. A major contributor to Sync's performance was elevated airspeed generated through ceiling fan assisted cooling and controlled ventilation. The increased air movement enhanced convective and evaporative heat transfer around the occupants, reducing perceived thermal stress even when indoor temperatures remained above conventional air conditioned set points. What's unique is that Sync achieves this by coordinating three systems simultaneously: the windblower for ventilation, the ceiling fan for air movement, and the air conditioner for targeted cooling when necessary. This demonstrates how adaptive comfort strategies can improve occupant comfort while reducing dependence on energy intensive cooling strategies. Overall, the simulation results validate the effectiveness of Sync's adaptive comfort strategy. Across all evaluated metrics, the combination of ventilation, fan assisted cooling, and intelligent coordination between the air conditioner, ceiling fan, and wind blower consistently improved comfort while reducing energy demand. These findings establish a strong foundation for the next stage of development, which will focus on pilot deployments and real world monitoring in occupied residential environments. This transition from simulation validation to field validation will allow us to further refine and optimize the system before commercialization. Having established the technical potential of zinc, the next question becomes whether this performance can translate into meaningful value at scale.
So, our pricing analysis was carried out using economic value estimation to quantify the value derived to the customer rather than simply adding the profit margin. The analysis shows that zinc generates approx 11,099 rupees of measurable annual value through electricity savings, lower maintenance, and extended AC life. However, the manufacturing cost is coming around 10,800 rupees. Shown here represents a prototype built using low volume fidelity methods. As we program to pre-commercialization, component standardization, bulk procurement, and optimized manufacturing, we are expected to reduce the production cost to 4,000 to 5,000 rupees. Therefore, while the EVE validates the product value proposition, our target commercial launch product is around 4,999, making the product affordable, competitive, and capable of achieving payback period well under 1 year. At the current technology readiness level, 17,499 represents the economically justified value of the prototype based on EVE. Beyond creating a value for individual customers, Sync addresses a significant market opportunity. Our total addressable market represents 43.5 million households across Indian warm and humid region. Our serviceable available market focuses on 17.4 million urban and semi-urban homes with existing cooling systems. For our final scale-up, we are targeting realistically serviceable obtainable market of representing our first 5,000 households and 1% capture. Combined with ROI of 344% in 7 years, payback period of 18.9 months, 63% product intent, Sync demonstrates not only strong customer value, but also scalable and commercially viable business opportunity. For our initial 3-year rollout, Sync will operate exclusively on B2C model, directly targeting middle-income households to rapidly secure our beachfront market. This lean to direct-to-customers approach drives strongly and financially viable. In 2027, we project a baseline revenue of 0.87 crore, yielding gross profit of 0.33. This guarantees robust profit margins while efficiently absorbing scaling operational costs. Under SDG 7, affordable and clean energy, target 7.3 calls for doubling the global rate of energy efficiency improved by 2030. Sync responds directly to that. Under SDG 11, Sustainable Cities and Communities, targets 11.1 and 11.b, calls for better urban housing quality and resource efficiency. We respond with the genuinely zero renovation retrofit. Next. Beyond the household economics, there's a real environmental and human story here. Each Sync unit prevents an estimated 820 to 900 kilograms of carbon dioxide emission every year by cutting down 1000 to 1100 kilowatts of cooling energy use. But the number that only matters to the people who are living in the problem isn't carbon, it's the sleep. Our research shows that 63% improvement tied to sleep quality, indoor air quality, and occupant well-being. Next. We have broken our proposed incubation year into 4 clear quarters, each addressing different questions. Quarter 1 is technical maturation, building a high-fidelity, full-scale prototype with refined housing and optimized airflow. In Quarter 2 is field validation. We deploy 10 to 15 pilot units directly into households in Udupi and measure real energy savings, comfort, and durability. Our Quarter 3 is pre-commercialization readiness. We lock in manufacturing partnerships, bring in our material cost down to a target of 4,000 to 5,000 rupees per unit through scale and prepare certification and industry-ready documents. Quarter 4 is scale-up, expanding from individual homes to rental housing, hostels, and homestays, while laying the technical groundwork of solar-powered, app-controlled, AI adaptive, and machine learning to make it more personalized.
So, with validated demand, strong technical performance, and a rapidly growing cooling market, we believe that Sync is ready for incubation and commercialization. The support of partners, mentors, pilot stakeholders will help us transition from a successful prototype of a scalable market ready or to a scalable market ready product. To conclude, Sync is more than cooling device. It is a climate responsive retrofit platform that synchronizes comfort, energy efficiency, and sustainability for India's warm, humid future. And let that sink in. Thank you, and we look forward to answering your questions.
Thank you for the presentation, Team Numa. You finished like right on time there. So let's move on to the jury members for the Q&A session. Yes, since you're on the aisle, I'll start with you. Press and hold. Press and hold.
Yeah. So, nice presentation, team. And I'd like to start by saying that the idea itself is very interesting and very practical also. So there is potential to the idea, and if done well, we can see real savings in the household with this idea. Now, I need certain clarifications. In your simulation, I think your technical testing was simulations only, right? Yeah, so in your simulation, you said the baseline indoor temperature was 31.5 degrees Celsius. Your baseline assumed an air conditioner, right?
Yes.
So with an air conditioner, how did the indoor temperature stay at 31.5?
The air conditioner was present as a unit, but it wasn't functioning at the moment.
So then
So
why is the power consumption 1.8 kilowatt hour?
it is when we talk about the baseline condition, when simulating it, the air conditioning works. We've taken the energy when the air conditioning is working throughout the night for all the 8 hours for 365 days. That was how we came up with the 1.8 kilowatt hours energy consumption. When we introduced sync into the simulation, the energy then, because the AC consumption.
Let's leave sync out. When your baseline is assuming that air conditioner is on
Yes,
for 8 hours,
yes.
then how is the indoor temperature still at 31.5?
We have simulated it against what would be
Just go back and check those
yeah,
numbers.
yes.
Second, you are saying your current BOM cost is 10,500, and at scale you think it will come down to say 4 to 5,000.
Yes, sir.
Uh, what will change? How do you plan to bring this down?
So now we bought it at the retail price. When the production increases, the bulk quantity pricing is going to change. And now the low fidelity and uh, what it actually costed to make the prototype was the pricing which we have mentioned now, the material cost and
What all
everything.
gets included in 10,500? What do you provide to the user?
So what we provide is this window unit, of course, and a control pod which will connect to the AC and fan. So for the fan, the normal fan has a regular regulator. So we'll change that to a wireless smart one, which will connect to the pod, and which the pod connects to the window attachment, the fan regulator, and the AC, so that all the three of them can work on sync. So what you get in 10.5 is this window attachment, the regulator, and the pod. Which
And where are the sensors?
the s-
So the sensors, there will be two sensors, one outside the room and one inside the room. So basically, the difference between there is a ton of calculations involved in this. Basically, we take the value of room temperature and also the humidity, and then we find the
One of the diagrams that you had that showed about 4 sensors in the room at different locations.
yes,
One near the air conditioner, one outside the window, one just inside the window.
yes.
So there are essentially 4 sensors, and just the hub and the window unit won't comprise the full product.
Sensors are just two, sir. The rest are the ESP module, which we'll be using in order to communicate with the pod.
But that also will be sold to the customers, right?
Yes, yes, of course.
So essentially, how many separate units are you selling to the customers?
Okay, so there is a pod, and then there is, of course, this tangential fan unit. And then if they want to integrate AC, they can have that option as well. That will that is +1. And then there's one for the ceiling fan, as you said. The ceiling fan, the microcontroller will be communicating to it wirelessly
No.
through
So
the regulator.
with all of these units, are you still selling it in 10,500?
Present value is present value with EVE. We got it for 17,499.
That's
The material cost was including all this, sir.
all of this.
Yes.
Okay, and how many ACs are you supporting?
Currently, we have designed it in such a way that it is controlling only one room. But in the future, we are looking at cases where one smart controller can.
One AC only within the room, but which brands of ACs are you supporting?
Currently, because we are doing a wireless protocol, any AC that supports the wireless protocol can be integrated with this.
It's not that straightforward because most of the ACs that are available commercially, they will not have open source their communication protocol.
So
how do you plan to support them?
So you can actually use it for any AC, sir.
But how do you plan to?
Yeah, that
AC has distinct IR codes. How do you get the IR codes?
So are you asking about the technicality of it?
Technicality.
Yeah, so basically we'll be using relay modules, and the relay modules will be connected to the controller we have used is ESP. So ESP has this wireless communication protocol called ESP now.
Yeah.
So let's say there is one, for simplicity, there's one main ESP controller. Let's say that is the heart of the entire system. And then there are sub branches. There are different other ESP32 microcontrollers, which will be connected to the fan. The
relay module will only turn on, turn off. So you are not considering temperature change of this.
Temperature change, there are only two sensors. So that is one outside the room, and then there is inside the room.
AC ka temperature change.
AC ka temperature, you can do that, but as of now, we have not considered it.
Got it. Got it.
Thank you, Yash. Swati.
Guys, a very innovative product. I congratulate you on coming up with the idea and trying to put it together. So very well done on that front. I have a few questions. You're saying that you are looking at 80 to 100 meter cube for approximately a 30 cubic meter sized room, right? So how do you know that is right? That is enough?
We have taken a standard bedroom condition to simulate it. So generally, most of the bedrooms that we have looked at in middle income houses and lower income houses, they had smaller bedrooms. So that's what we simulated.
It's not the bedroom size. I'm talking about the ventilation rate. How do you think 80 to 100 cubic meters per hour is enough?
Currently, what we have done is we have sensed the number of occupants and then introduced ACH into it according to the requirement. So when we're sleeping, the required ACH is about 0.7. So we are looking into how to that gets coded with the
is it based on a code? Which code did you follow
we use
for the ventilation?
We use the standards, the ISHRAE standards for the ACH and the minimum ventilation rates.
Okay. All right. Okay. What simulation tool did you use for the simulation? You said everything is simulated, right?
Yes.
So what is the tool that you use to simulate? Did you use a analysis tool? How did you simulate it? Because your whole product, everything is based on simulation. So how did you actually simulate it?
We used some. We had some design builder.
Go on. No.
I think it was design builder.
Did you use design builder?
Yeah, for the modeling of the space. And we yeah, we had to manually change the internal conditions, but yeah.
So how did you manage to do this dynamic control of, various systems using Design Builder? Because Design Builder itself doesn't have an automated way of changing, your
Yeah,
control
we
parameters.
basically came up with a logic of how the smart controller's logic, and then put that into it, and then simulated, because we already had the logic ready. So then we simulated the conditions at, like, we set the room temperatures and the conditions for the whole unit to work, and
Mm.
we found that it was under proper thermal uh, comfort.
So when we look into the psychometric chart, so the temperature and humidity along makes a comfortable. There is a comfortable zone in the middle of the psychometric chart. So we tried to make a simulation, reach that point of humidity and temperature using all the appliances in the room. Basically, that's the base idea.
Okay, and you use Design Builder for it. Okay. All right. One question. You're having your inlet and the exhaust in the same panel, right? Do you think there'll still be distribution of air across the whole room? Won't it short circuit?
Divided also.
Yeah. So same pattern as in this is a separate compartments there. So the exhaust and the inlet are not mixing air or anything. And speaking of if it's enough for the whole room, the exhaust actually it's a subtle exhaust. It's not a full blast it's not like a kitchen exhaust or anything. It just removes whatever humidity and temperature necessary, and the room won't be boiling. And also to mention, we are using the AC and fan. It's not like we are replacing it. So with the help of AC, fan, and this, it will be much faster rather than just focusing on the AC or on the ceiling fan or on this product altogether. So
So the most important thing that I noticed from this is you're providing ventilation into a sealed room, improving the indoor air quality, and as part of that, as a byproduct, you're able to control the humidity entering the room, right? But the most important thing is the ventilation, right? So one of the important things that we gave in my feedback is also you need to consider the CO2. The main impact is you're able to control the carbon dioxide in the room.
yes, ma'am.
So it'll be good for you to measure that to start with. Design Builder allows you to do it. My question is, you have an inlet, you have an outlet. Air takes the least path of resistance. It is not going to come in, distribute around the room as per your arrows of hope and go back out of the exhaust. It'll happen locally. So how do you ensure that the air distribution happens through the room?
We are using it most of the time. The modes where it operates only on ventilation, it's given the conditions, climatic condition, it's going to be very less. Most of the time, it's going to be used along with ceiling fans itself. So the elevated airspeed can help in the movement of the air through it.
Okay. See, that also requires simulation. You need to do CFD simulation to understand how the distribution happens, at what speed you need to, that fan, inlet fan has to work, and at what speed the outlet exhaust has to work and how. So that also needs to be designed properly, otherwise it will not work, it'll just short circuit.
Yeah.
Okay.
We have also included, for now, for the prototype, we haven't included the fan speeds. The fan speeds are supposed to change according to bring the occupants to the required thermal comfort. So because we are providing the regulator as well, so that works in conjunction with this.
Okay. So I'll just wrap it up. Great idea, but I think you have a lot of, way to go, even in your simulation methodology. Yeah.
Thank you, ma'am.
Thank you, ma'am.
Thanks, Swati. Kshitij, slightly over time. So if you can keep it a bit short.
Just one question. I have 5 here, but I'll ask one.
I can give you 3.
Thank you, team, for presenting. I think it's a very interesting approach that you all have taken almost it's taking a very first principles approach of solving the problem of humidity, ventilation, cooling in a particular room. My fundamental question is, this works for people who have an AC?
Yes.
What problem are you solving?
AC is the energy consumption in general.
Who has that problem?
The middle income households.
Do they? We have that problem. We are able to, we understand what energy consumption is. But do you think people are concerned about it?
The electricity bills are going to reflect those.
So what problem are you solving?
We're solving the
Energy, money, what problem are you solving?
We're trying to save and conserve energy, which in turn conserves the money economically also. So
it's not a comfort problem.
We're making it affordable cooling strategy.
also, sir, talking about comfort, what people usually do is just turn on the AC the whole night and then close the windows. Even if it's like cold outside, they turn it to 16 and sleep, or they turn it to 24 and sleep. But to reach the comfortable place, we don't really need to go down to 24, go down to below 24. 26 and fan on 3, that's enough. But to simulate that differently, we have automated the whole system, so we don't have to like manually. So people don't really change the stuff because it has to be manual and they have to continue. But if they do introduce sync into the system, all of this happens automatically. That's the base idea of it.
So as I said, I think you all have had an interesting approach. There's a lot more thinking that needs to be done, right? If I've spent 35, 45K on an AC, I'm not expected to spend another 10, 20 on this particular unit. For what is the question? Am I really getting that much savings?
So the market price later, as explained in the incubation,
5,000, 8,000.
5,000, yeah, that's the max we are trying to go.
Yeah. So I think that's where the challenge is, because you're targeting a market that already has an AC. But if you think of this as a completely integrated solution for people who are just trying to install an AC and pitch to them, I think your target market is slightly different.
Yeah, thanks a lot, Shadrik.
Thank you,
members. Yeah.
Thank you.
Thank you, Team Numa. You can take your seats.
Thank you.
Thank you, everyone.
We'll take a quick short 5-minute break. And I request Team Numa to move the prototype outside, and the next team to move their prototype in. Team Solar, we stopped, right? Team Solar Alchemists. Yeah, we need to move your prototype in. Yeah. I was just after the first presentation. I was like, kindly tone down the length. That's it. That's it. Only the time. That's it. I know. I should have done that.
Restricted us to one question.
That was the last person who gets it. Typically, it happens to be that way. Next team, you will start first. Rotation.
For demonstrating the model, we have housed the unit in indoors and internal and outdoor, indoor and outdoor unit together. Outdoor can retrofit.
कोई नहीं यार हमें नहीं आता है 20,000 और 15,000 15,000 का दे देंगे मैं समझ सकता हूँ what I can do with my student with saving 1 unit of energy what am I going to do I can't comprehend whatever unit whatever kilogram whatever you put for a lady is 1 second you go what because car going at say currently 1,050 max speed, right? And I'm designing something goes at 100. I'm able to beat it. I know what you're saying. But 50 का 51 होता है. एक का क्या करें मतलब? हाँ, data entry. Data entry. Data entry. Chemistry.
Ready, Team Numa? Sorry, Solar Alchemists. You guys can be seated. I'll call you. Turn the table slightly. Slightly turn it. The table is also okay. That's enough. That's enough. Yeah. Yeah, yeah. Shall we? Yeah. Guys, ready? We need to start. Yeah, I'm ready. Let me know. Guys, let's settle down. Yeah. Okay, so our second presentation today is from Team Solar Alchemists. Their product is Archaea. It's a solar powered air conditioning system with a DC compressor. Team Solar Alchemist, could you please take the stage? This is next back. There's no laser. Right. So, team, you have 20 minutes for your presentation, and it will be followed by a 10-minute Q&A. Right. So, you can see a timer here, and at the end of 15 minutes, I'll give one bell to let you know you have 5 minutes remaining. Okay. So, at 20 minutes, if you have not stopped your presentation, I'll have to stop you. Okay. Good luck, and your time starts now.
Good morning, everyone. We are Team Solar Alchemists from SSN College of Engineering, and we are here today to present our product, Archaea, a solar-powered DC retrofit air conditioner. Our team comprises of a holistic members from mechanical engineering, energy engineering, an MBA student, and electrical engineering. So, let's have a look at our product. Let's consider, let's put ourselves in the shoes of someone to understand the real problem that exists today, right? So, in Chennai, let's just imagine a middle class family headed by Dr. Kumar, right? So, he knows what turning on the AC means, even though it's very hot outside and his family awaits and everyone is trying to sleep at night. It has been a really hot and humid day, and if they turn on the AC, they know what that means for them. It is a huge increase in the electricity bills that they will need to pay for that month because of the AC, right? So, most middle class families in Chennai tend to hesitate a lot when it comes to using AC. So in Chennai, to establish, we are using Chennai as our experimental area, right? So who is the AC? Who's being affected by this problem, right? Most middle class households are the people who are struggling to use AC, who really have to, uh, compromise either cost or comfort, right? And why do existing solutions fail? Right now, inverter ACs are kind of expensive, plus they running cost remains consistently high, right? So you need around 35 to 60K to buy one, and then because of its high reliance on grid electricity, it tends to get quite expensive throughout. So running a inverter AC is something that they hesitate to do. And if you have a solar hybrid AC, first of all, it has very high um, upfront costs because solar technology isn't always cheap, especially when you have to hybridize. And additionally, it has a longer payback period because of its high upfront costs. And air coolers are ineffective in 70% plus humidity, which is very common in Chennai. And BLDC fans do not actually offer any actual temperature drop. And the main thing over here, right? So in Tamil Nadu, there is something known as a slab-based tariff system. Okay. So what this means is that the higher number of units of electricity you consume in a month, the higher your cost per unit becomes. Okay. And in that also, there are two categories. One is your below 500 consumption, 500 units, and above 500 units of consumption of electricity per month. Okay, so let me give you an example. If you've consumed less than 500 units, there is a separate slab-based tariff system which will say you consume around 400 units a month, you will be charged around 950 rupees, so around 1000 rupees, let's say. Okay. Whereas if you've consumed 600 units, so just 200 units more, you've unfortunately crossed the 500 unit mark, which means that per unit you will be charged more, which means you will be paying around 3000 rupees for a 600 unit consumption per month. So just think about it, right? 400 to 600, just a 200 unit jump. However, you're paying 3 times the cost. And how is this? And usually this jump between 400 to 600 is caused by the AC, use of AC. So the one thing that people have missed, right, is the compressor. It uses like the majority of power in an AC is taken up by the compressor. Whereas if you have a solar hybridized AC also, solar makes DC, which means they put a inverter in to change the solar power from DC to AC, AC as an alternating current so that the compressor can run. This also has a conversion loss, and therefore there is more energy loss even in case of a solar AC. So conventional ACs usually use an alternating current compressor, and even if you use solar, it needs an inverter. So our innovation was that why not just eliminate first of all the inverter so that we can eliminate those 5 to 10% losses, and also why not have it run on DC so that it can directly be powered by solar. So our singular retrofit can address a lot of problems at the same time. First, so what does it consist? What does our solution consist of? A solar panel, a 48-volt battery pack, an ESP32 control module, a DC compressor that will take around 400 to 500 watts to provide 1 ton of refrigeration, and this includes the energy that will be consumed by the DC motor in both the condenser and evaporator, and an indoor evaporator that pretty much remains unchanged except that it will now be run by a DC motor. So our product will work on 2 cycles, a day cycle and a night cycle. The solar panel will charge the battery pack during the day when most, and this is another observation, practical observation, is that in most middle class households, no one will be at home usually during the day because children will go to school and the parents will be at work. So the main demand will be at night. So during the day, the solar panel can charge, and during the night, it can discharge, and the stored energy will be consumed by the AC. So we conducted a thorough user research. We put out 250 Google Form surveys. We had in-depth interviews, and we also considered some secondary research. And our key findings were always consistent. Most users were willing to spend some upfront cost if it meant that on the long term, they will have a significant reduction in their monthly AC bills, electricity bills. So, why our AC is a genuine innovation, right? First of all, as you can see in this table, for 1 ton to provide 1 ton of refrigeration, we are using a lot less power, and ours is DC compatible and it can be run by solar. We have a lower inverter. We don't have any inverter conversion loss because we're not using an inverter, and our power saving is also pretty high, as you can see when compared to the baseline conventional ACs. And when compared to BLDC also, we have less losses, and our payback period is also going to be lower. And in our feedback we were given, during one raised a valid concern. Most ACs today are BLDC. We agree. We are trying to compete with BLDC ACs, or we are trying to retrofit existing conventional ACs. Thank you. Over to Lavanya for.
From building a concept to a fully functioning prototype, we were in requirement for 3 subsystems. The first one was the mechanical frame and the refrigerant circuit, which includes a structural framework, the DC compressor, evaporator, condenser, and all the expansion valves. And the second thing was the power source, for which we used a monosilicon solar panel, a solar charge controller, a 48-volt sealed battery bank, and a DC bus. And for the electronic modules, we used the ESP32, the humidity and temperature sensors, and a dashboard. So the first step was to calculate the load. So we considered a room of 8 cross 8 cross 8 feet, so which is around 12.8 cubic meters of volume of a room. So in that room, it was housed with a lot of different materials. We had a wall which was exposed to the surroundings, which had a load of 371 watts, and we had a lot of glass panels, which was around 320 watts, and the solar radiation from the roof and from the walls, which was around 540. And the internal heat loads, considering the people, we considered 2 peoples and all the appliances that produce heat, which was around 220 watts, and the infiltration and ventilation loads of 270 watts, for a total of 1700 watts. So we know that 1 ton of refrigeration requires 3.5 kilowatt of power, heat. So for 1700 watts, we designed a system for 0.5 ton refrigeration. And we also validated our data using CFD analysis to analyze the flow pattern and the temperature interaction between the rooms. So we had 2 cases. For the first case, it was with the conventional AC, and the second case was with our design system. We used an optimum air velocity of 0.05 meter per second, which requires a motor which has to be run around 300 to 400 RPM. So for which we chose a motor that was around 100 watts. So we used the motor to achieve the human and the thermal comfort inside the room. So next comes the integration of solar power. So the integration process involves the coupling of the solar PV with the air conditioning system. So during the periods of high irradiance, the PV system supplies the power directly to our air conditioning unit, and the excess energy was stored inside the battery. And when additional power is required, we can also integrate it with inside the grid. So here comes the basics of vapor compression refrigeration cycle, where the low pressure refrigerant from the evaporator goes to the compressor, where it attains high temperature and pressure, and then it goes to the condenser, where the high pressure vapor is cooled to a liquid and the heat is rejected to the environment. And then from the condenser, it goes to the expansion valve, where the liquid refrigerant loses pressure rapidly. And then the liquid vapor goes again to the evaporator, where it absorbs the heat from the surrounding and then it sends back to the compressor, completing the cycle. So the performance of a system is evaluated using the coefficient of performance, which is the ratio of a refrigeration effect to the compressor work. So basically, the vapor compression cycle is unchanged. We only modify or change the conventional compressor to a DC motor powered compressor.
So while coming to the prototype and modeling of the entire systems and all, so we have taken a dimensions of 8 into 8 into 8 feet of room spacing for a middle basis level. So on the cases of we are having some 3 shield windows and 4 side walls on top of roof, and in that we theoretically design some models of the refrigerator means air conditioning systems comprising of the basic components. So next, please. So the integrated system includes solar panel, which reduces the power from the solar radiations, and it has been optimally controlled by MPPT, which is a controller, and the controller which drives the power to the DC compressor, and the entire refrigeration systems will run. In that cases, if there is a much sufficient amount of solar radiation is present, means the controller will directly converts the energy from the panel to the DC compressor. If cases of night, so or the minimal solar radiations, on the time the controller will get the power from the battery bank, which is probably 2.4 kilowatt hour as per our cases. So the entire systems will run on day and night basis. So in the cases of simulation part, the first one describes the temperature and velocity profile of the room we have been taken into considerations. So and in addition to that, the vector flow field, how the velocity has been concentrated on the entire room space. So we have studied on that, and we optimally made a prototype accordingly. So next. So in that in that model, we have added the basic necessary components in accordance. The main thing here is we have stacked the outdoor and indoor unit compactly, so for the demo purpose. But in real cases, it has been differentiated at 2 different. So shall I'm just describe the components and working. So we are having a DC power source instead of a solar panel based MPPT controller. So in the dashboard, we are having some temperature indicator about the evaporator, means coming out of the air, and we are having a simplified form of maximum mode and echo mode to describe the comfortness accordingly. So and we are having a power source of 24 volt and 5 amps as the input power. So we can differentiate according with the mode, high, medium, and low. So and the temperature rising and decreasing purpose, we can alter it and done it. So here we have majorly changed what is the compressor, DC compressor instead of an AC one. So next, please. So while coming to the testing part, we have done a testing of 7 days, irrespective of the timing. And in that 7-day interval, we have done we got units of power consumed accordingly, and the grid reductions we got around 70 to 80% instead of 60 to 65 to 75%. So we got the average energy savings of 74%. So coming to the next with Vishal.
So yeah, however good the engineering might be, price is what matters to the Indians the most. So like, however you go, so this is your product pricing. So first, let me say these are the core components. It's the DC compressor, the solar panel, and the charge controller, and then the refrigerant fill and labor. So the consumer price is 24,500. So and then if you add the profit margin and then the everything, it comes around to 34 to 38K. So now all of you might think I could buy a new AC for this cost. So like what we are going to pitch in is we are not going to remove the existing AC. So this price is inclusive of the solar panel, the battery pack, and then the compressor. So once you buy this and you fit it inside, you will get your ROI in 3 years because based on the usage patterns and then the slab tariffs, you could save around 10,000 to 15,000 per month. So you're initially investing around 35K, let's say. So within 3 years to 3.5 years, you'll get that money back. And then after that, you won't need to pay the EB bills at all. So, and then we also did user testing. So since the time is less, I'll go above fast. So these were the responses which we got. So these were limitations, like basically the cooling response felt slow. So what we are going to do is improve the blower fan speed. The second one was the humidity is still visible. We have actually already incorporated in this. We have kept a desiccant layer to control the humidity level over here. And then the dashboard was appreciated. And then the compressed sound is still slightly noticeable. Since this is a bit of a demonstration model here, you cannot hear the sound. But then in the actual testing prototype, the sound was actually pretty much audible. So we need to control the noise as well. And then, yeah, so whatever product you buy, a value also comes with it. So this pyramid basically explains that the economic value, functional value, emotional value, and societal value. So yeah, we'll go on to the next. So how we actually came up with the price. We followed the 6-step approach. So first we understood the user pain, and then we went with the market price, and then we estimated the prototype cost, and then the energy savings which they would be able to do, and then their willingness to pay. This one we got from the user research during D1, and then finally we mapped the value. And then, so if you look into our prototype, you could see into 3 impacts. First one is the household. So as a person, I won't be needing to pay EV bills if I put into a solar panel. And then next one, this will also reduce the grid impact. So the amount of power consumed, if you're going to be using a solar panel, will start to reduce. So this directly relates to the Sustainable Development Goals 7 and 9. So yeah, this infographic basically explains the whole thing. So usual AC has an inverter and there's 15% of energy losses. Ours does not have any loss. So conventional AC compressor gets around 1.2 kilowatt hour, whereas ours is around 400 to 500 watts. So you could run it 4 times more. And then SDG 9 is basically industry innovation and infrastructure. So we are improving the temperature cooling efficiency and then the humidity control. Right now, we are moving towards TRL5. So this is essentially the case for incubation. So yeah, I think the time won't be enough. Next one. Next. So I'll just finish on a strong note on water resistance. We initially started with people, not technology. We started and met people, understood what their problem was. Most of them was like, we'll put AC for half an hour and then switch it off. That cooling is enough. We don't want AC for like 2 hours. You need to pay extra bill. So that's where our spark started. We started with that idea. We found out the culprit was the compressor. And then we started that should switch the compressor into something that does not consume power from the grid. So that's where our idea started. And then we actually built a prototype that works. We have 2 prototypes. This one is the demonstration one. And then the testing one is right there in college where we did all the testing. This one, due to transportational issues and the refrigerant gas, we had to fill only like around 70% of the gas for safety reasons. And then this market has not yet been explored, like retrofittable. Everyone goes for new AC. Like right now, our product, you just take out the compressor from the outdoor unit, switch it back, and then you can run it for like next 7 years and you don't need to pay the EB bill. And then you'll get your ROI in max of 3 to 4 years. So I think this is where we stand out different. And yeah, thank you for the opportunity. And just a minute, the last slide, we'll come back to Kumar, like who we started the first. So right now he sleeps freely, like no issues, just to finish on a positive note. Thank you.
Great presentation, guys. Good timekeeping there. I'll move to jury, and I have learned my lesson.
Hey team, good presentation. Thank you for taking the effort to put together this presentation. I have a few clarification questions. Is this for independent homes or is this for apartments?
Yes, both cases it will be applicable.
Even apartments?
But
100 apartments in a building.
We are limited with 1 BHK spacing.
I get where you're going. If in an apartment,
Where do I put?
panel,
Yeah.
So that might be a problem. We were also thinking of that. We haven't found an like a sound solution to that right now. But then if an apartment has like not gated communities right now, I don't know the solution for that. Like for gated communities, you need to get approval to keep a solar panel above and then bring in the line. But then if it is a 6 or 7 house smaller apartment, because in Chennai, the number of gated communities are right now starting to go up. Otherwise, most of the buildings have around 7 to 8 houses only. That time, I think keeping a solar panel above won't be much of a problematic if you come into a.
Okay. And what you're saying is you're selling the compressor. What do I do with my existing compressor?
The existing
So usually we are replacing that existing compressor with the new one.
You'll take it away.
So
I've spent 35,000 on that,
as
and
in-
now again you're asking me to spend all this.
No, sir, no such cases. We are giving it as a new or old product with a retrofitment segment.
Okay. Last one. Just wanted you guys to think about this. You're encouraging AC usage,
Yes, sir.
right? So let's assume currently Kumar is using it for 2 hours. He'll use it for 6 hours. 40 million homes are using ACs. You're moving it to 120 million. What do you think would be the side effect of that?
So yeah, the emissions will increase, but then I also thought the same thing before coming right here. So what I thought was typical Indian mentality right now is if I do something, it's not going to affect the whole way. So
So in that case, how is it aligned with
sorry,
one
that
of the
came out so
SDGs
wrong.
that you
That came out
mentioned?
so wrong. So comfort matters more to us. Like, let's not care about the environment. So I think
Fair enough, I agree. But then how does it
no,
align
I'm
with
not
the
talking
SDG
about
that you've
myself,
listed
but
there?
then, the user case. Like right now, when we went and spoke with the people, they were like, "I just need cooling," and then I want it for free. So that was their mentality. I think we need to innovate more in this to reduce. As of now, we'll be reducing the grid impact. So the amount of power we are getting from the electric substations would be reduced. We are shifting more towards renewable side, but then the emissions that will be coming from the AC would still be there, and that would increase. So it's basically a trade-off between those two. I don't know if we'd be able to cut off the emissions completely.
SDI, another division challenge.
Commend you on your honesty. Very, very honest answers and a very well put together, honest attempt at what you want to do. So I have a couple of questions. You said solar panel. Have you considered the cost of, even in an apartment, maybe you can position the solar panel on a south, as a chajja or something like that over a window that cuts down the heat into the house as well. So maybe there is a potential to integrate one solar panels or two solar panels. But have you considered the cost of a battery? Because all your test cases are daytime. What about nighttime testing? Because that's when it will be used the bedroom.
Yeah, ma'am. At that cases, we need a battery pack.
Yes. So have you considered that cost inclusive?
The batteries can also be used as a UPS support.
Yes, absolutely.
So that cost, the battery cost, we need not to spend especially for this. So separate, we need not to spend money for a battery pack. So that battery pack can also be used as a UPS supply system for the entire home.
But most homes would not have that. So you're adding that extra cost into their household.
So in that cases, we have been getting a payback period or a return on investment on the by reducing the consumptions of the electricity from the grid, ma'am.
No, that is true.
Most of the Chennai homes do have UPS. Yes,
Okay.
we do
All
have
right, middle
UPS.
income
Most of the homes don't even have Wi-Fi, but they do have a UPS system there because of the power fluctuations and the.
Okay. All right. Your heat load calculations, what is the size of that room that you have considered?
8 feet, 8 feet, 8 feet.
8 feet. Isn't that very small for a bedroom?
Yeah, ma'am. For a test case purpose, we have taken a 8 into 8 into feet. 8 into 8 into feet. So for a larger scale of user testing, we can go with around 12 into 12 into 12 feet also, ma'am.
Okay.
So that comes in our case to incubation. If we had time, I would have explained that, like the scalability part. So like when we are approaching towards TRL 6 or 7, actually testing it in real households and bedrooms which are bigger than 8 feet into 8 feet. That time we would do moderations into it so that the appropriate cooling achieves in the required amount of time.
Okay. So for an 8 by 8 feet room, your heat load seemed quite high.
Because we also included the battery pack inside. So basically solar panel also would be connected to a battery source, right? So we kept that battery inside and also considered that. So that's why the heat load was actually pretty high. And then there weren't two people actually inside. So we assumed that. And then the battery pack. These two were the main culprits for that heat in that room.
Okay.
To attain a better COP also, we have assumed that heat load as more, ma'am. So,
and what is the external temperature at which you have been calculating this heat loads?
Means temperature difference?
What is the temperature difference between inside and outside?
Yeah, ma'am. For out, we consider as 32 degrees Celsius, and in 24 degrees Celsius we are taken.
Okay.
To maintain temperature on the evaporator of the equipment, we are maintaining as 24 degrees Celsius.
So external temperature you're considering as 32.
Yes,
But
ma'am.
in a middle income group housing at 32 degrees, they'll only use a fan. They won't use an AC.
By considering fan?
They won't at 32. If the outside temperature is 32, they will not use an AC. They will only use a fan.
Chennai also has a humidity problem.
I know fans take care at 32 degrees it does, but Chennai also goes up to 38, 40
Yeah,
degrees. So that is when the AC comes into play. Right. So your consideration for heat loads as well as your compressor should be dependent on that temperature and not a 32-degree temperature.
Ma'am, we can shift up the temperature differences also. So initially, for this case, with the temperature difference of 32 and 24, we are putting input power as 250 watts. So if we go high means we can shift the temperature difference to 38 to 26 also, ma'am.
It's okay. All right. Yeah. But yeah, you can't, your test case, your costing, your savings should all be based on that.
Yes, ma'am. Yeah.
In a middle income group at 32 degrees, even if you look at National Building Code and comfort charts, 33 degrees with fan at 70% humidity is within the comfort band or at the edges of a comfort band. Right? You should go beyond that. All your calculations should be based at a high number. Okay.
Thank you.
Thanks, Swati.
I'll come back to the battery point. You said that a lot of houses have UPS systems, inverters already. These are designed for power outages, right? And they are not expected to be used daily. Have you calculated the life of this battery? So every battery has a fixed number of charge discharge cycles. After that, you have to replace the battery. EVs also have this problem. After a certain number of years, you have to change the battery. In your system, have you considered the cost of replacement? Your payback period will change drastically if you include the battery cost every couple of years.
So we have not taken this part into for calculation purpose, but we believe that that UPS battery having a life period of 8 to 10 years of liquid.
That's assuming very infrequent power outages. They are not designed for daily use.
Yes, sir.
Right.
So we can.
Yeah. Second thing, you mentioned MPPT several times. MPPT itself requires a lot of equipment. You need to keep tracking the sun's position and all. Has that all been factored into your cost?
So we can add up any kind of solar tracker also. So initially we are facing it towards the south positions. So
but the solar tracker motor, the entire assembly, all of that adds to a lot of cost.
Yes.
Has that been factored in?
We have not included that tracking system, sir. Yeah.
So then the calculations that you have done over there, you have included MPPT, right?
Yes, sir.
You have assumed maximum irradiance and maximum power generation. So that won't match up. And finally, what's the market size you're looking at? You agreed that BLDC based compressors are now, what is being sold. So you are essentially targeting a shrinking market, right? Anyone who now purchases an AC is going to use an inverter, BLDC compressor based AC. So why should, coming to the case of incubation, why should an investor invest in your business when the market itself is shrinking down?
So to address your question, first of all, on the retrofit segment, we are actually targeting conventional ACs, but you're right, that is a dwindling segment. But more than that, we are trying to compete with BLDC ACs. So right now, we are trying to offer a solution that is going to be.
I'll just counter your point over there. Yeah. Your system is costing about 30,000, and that's on top of an AC. You're saying you're not replacing the AC, you're just retrofitting it.
So the retrofit is in case of a conventional AC. But in case of BLDC ACs, we would try and manufacture from scratch. So we would offer our own AC basically.
Okay, I am at the end of my time. So basically, if you are selling your own AC, what will that be priced at?
So that's the thing. So right now our main point is that we are able to reduce the long-term cost for the family, right? So in the long term, a BLDC AC would still cost them more to run it on a regular basis. Whereas our AC, because it's solar powered, it will cost a lot less. So that is our main competitive advantage over a BLDC AC.
Okay. Okay.
All right. Thank you, jury members. Thank you, Team Solar Alchemists. You can take your seat. Yeah. So we're going to take a small tea break for 15 minutes now. And we'll come back with the third team. A tea is served right outside this hall. And it's 11:22. We'll be back at around 11:35. And the next presentation will start at 11:40. Okay. So see you in 15 minutes. And folks online, I request you to stay tuned so you can help support the upcoming teams.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool.
Welcome back to the Residential Cooling Retrofit Division presentations. So we're moving on to the third presentation of the day. This is a presentation from Team Shitansh. Their product is the Chill Sphere. It's a personal cooling dome for young professionals who are living in hostels and PGs. Right? Team Shitansh, if you can please take your stage. Right. Team, uh, yeah, you'll have 20 minutes to present your work to the jury. At 15 minutes, I will ring a single bell to let you know you have 5 more minutes remaining. Okay, you will not have a 21st minute. At the end of 20th minute, if you have not finished, stopped your presentation, I will continuously ring the bell so that you stop. All right. After that, we'll follow with a 10-minute Q&A with the jury. Okay, team. The stage is yours, and your time starts now.
Yeah. Good morning, all. I'm Ananta Krishnan. This is Saikat, Tattvam, and Keso. We are Team Shitans, part of Team Sunya from IIT Bombay. We are here to present our product, Chill Spear here. So the top left image, most of you, at least many of us must have seen that. India having the top 50 hottest cities in the world. So this is a fact which we are living right now. And this is actually enhanced by the urban heat island, wherein for a particular region of dense urban households, you can see that average temperature is much higher than its surroundings. When people generally go for air conditioning to actually solve this issue for them, what happens is that these air conditioners are also getting much more expensive as we go. And above all those things, if you look at it, there are certain hidden costs along with this air conditioners also. So what we like to highlight is that, say, our broad problem definition from this is that rapid urbanization along with urban heat island has caused, let's say, air conditioning as a health necessity, because of which there is this particular cooling gap, and certain section of people are more affected than the other. And one such demographic is professionals and students occupying PGs and hostels in such densities. Why? Because since they are living in such an institutional restriction, they don't always have the autonomy to change things around them. Then a lot of times when they work, their work hours align with whatever the peak heat load is happening, and also oftentimes they have to move cities, so they are very much reluctant to actually invest in a much more bigger solutions. So, and we are only considering warm and humid and composite cities. Why? Because 8 out of 10 cities in India is coming. 8 out of 10 dense cities in India is coming in this criteria. Our out of almost estimated 290 households in India, 270 non-AC households, and our market we are thinking of is 55 million of TAM, and only 100 units in the first year. When you look at the market, there are multiple options. Let's say split AC, window AC, and portable AC. And on the other side, we have ceiling and pedestal fans. So all of them has such stark difference. On one side, A pedestal fan is able to give you affordability, portability, easy to maintain, but it might not always give you the thermal comfort. On the other side, AC is able to give you the thermal comfort, but lags behind in all of this. So that's what we want to highlight there. There's an option, there's an opportunity for something in between, which is affordable and is able to give you the thermal comfort within that criteria. That's where we come in. ChillSphere, we are able to provide you thermal comfort for a particular microclimate. As you can see here, the person can come inside. As I sit down, as I sit down here, I am able to cool myself with the help of a cooling dome on top of me, which is being cooled with the help of a VCRS-based compressor, VCRS-based water chiller. The dome is cool and give me cooling in this only this microclimate. As simple as that. Okay. Now, from an obscure idea. So we are planning to place it at an MSRP of say 14,999, which much say almost 40% cheaper than an AC and consuming as less as 60% consumption against an AC. So from the obscure idea, we want to explain you, how we journeyed from the obscure idea to the prototype which you see in front of you while adhering to the contest complaint matrix. And also one more thing we like to address that certain reviewer comments we already integrated into our solution, and also certain reviewer comments were specifically mentioning in the slide and addressing here.
We did the primary and secondary research, and we find that cost, maintenance, portability, and institutional restrictions restricted the user to use the market available thermal comfort product devices in the market. They're restricted. So these are the pain points. These pain points are the main focus problems of us. So we did the qualitative research and participant observation and field note. This is called the ethnography. We did this process and we conclude our target personas. As we see, the Priya Sharma and Arjun Mehta, both one is a UPSC aspirant and one is a college student in Mumbai. They're losing their productivity due to these problems, due to these limitations, you can say. So we all need functionality where comes along with affordability. If there is no affordability, we can't do it's not good. So we come along, we empathizing their situations, we come with 10 possible solution, and we did some elimination criteria, and we come down with this elimination criteria, we come down one single finalized possible solution is a localized cooling dome. And so this dome is features like the targeted product is features to cooling the microclimate, high portability and easy to install, where the traditional cooling devices is available in the market is cooling is focused to cool the whole system, but our system is focused on to cool only the target persons or the target microclimate. Now, and we did the low fidelity mock-up and the vision board, or you can say the poster to what is called to behavioral observation and product interaction and product ergonomics. We also use the AEIOU framework to gather, categorize, and obtain the insights for the further prototyping. And for the prototyping, you can say, and our main important concerns are area, heat rejection, and working noise. And to these things are gave the directions for the further design goals.
So moving from an ideation to an actual product, we need to define a scale which can measure the parameters, and we have targeted the parameters such that for thermal comfort we are targeting that the room temperature should come between the 80 to 90% band according to the IMECR standard, and for energy efficiency the product should consume less than 50% of the energy as compared to that of 1 ton of AC. And we have integrated the following principle, which incorporates the human thermal comfort modeling, radiative and convective heat transfer, and VCRS system. So to make an actual active cooling product, we need to understand what cooling load we are targeting for. So for a microclimate, like a person is sitting on a chair and doing some light activity. So for that, according to ASHRAE standard, a person with having an average weight and height of this, it will emit around 108 watt of energy because of its metabolics. And we have assumed that the skin or a clothing temperature would be around 34 degrees Celsius. So moving from an considering the ideation part, we have iterated our product, and this one is the first iteration in which we have understood the ergonomics, how product is working, and also how water is flowing over the product. In second iteration, we have changed the shape from the curved aluminum rectangular sheet to the frustum shaped aluminum sheet, in which this is the water collecting part with the green color one, and this is the water chiller. And this water chiller will provide the cool water, and it will flow over the dome, and that will cool the aluminum dome. This dome will provide the radiative cooling to the person which is sitting, and on top of that we are providing convective cooling with the help of fan attached below it. This was the fully functional prototype. So for that we have experimented and gathered the globe thermal temperature, ambient temperature, relative humidity, and the air velocity. But it doesn't seems like an actual product. The product should be lightweight and more compact. So we have came to the third iteration, in which we have used CPVC pipe, which are light and compact. And also we have used the flexible duct to remove the heat from the cooling from the VCRS system to the outside of the room. And this one is the current iteration, in which from the technical part we have added this PLA based insulation system over the dome to ensure that the external heat is not penetrating into the cooling path of the water when it is flowing over the aluminum dome. And also to give more flexibility, we have added the wheels to the system to have a good mobility, and a user can adjust the height of dome according to its comfort. So this give much more utility to a user. But wait, does it actually work? So to test our prototype, we have used the IMECA standard, and according to that, these blue color lines are showing the operative room temperature, and we have tested rigorously for 3 days. And yeah, so our operative temperature was coming within the IMECA band.
So while we were testing, whatever comfort we were feeling under the dome, it was good. Everything was good, but we were feeling even more better. So we want to find that hunch, why we were feeling even more better than whatever we could observe. To see whether whatever hunch we had was not just a bias from our side, and whether others are also feeling the same. What we did, we asked other users to actually do the user testing for the complete functional prototype, and they also confirmed our hunch. And also they give us other insights regarding the thermal performance, acoustics, overall user acceptance of a product. Okay. And while moving ahead with the hunch, we wanted to understand how this product is physiologically affecting me as a person. So user was asked to sit under the dome, and we took a thermal image of the person. Then after 10 minutes of operation of the dome, we took another thermal image. As we compare both these images, we could see that just in the upper body where the cooling is being focused, there is a difference of say 0.3 to 0.5 degrees Celsius. So this results in literature is also relating to another major study by Sang et al. In UC Berkeley lab, wherein if you focus your cooling on the forehead and the carotid artery range, because of the number of veins there, number of nerve endings there, your body is feeling much more comfortable than it's actually feeling at that particular temperature. So a product has a much more physiological effect also.
Now that we have understood the technical results and the physiological effect our product has, we will move on to what is the value that our product creates for our customer. So ChillSphere defines a new category in personalized cooling by bridging the gap between ineffective fan and energy intensive AC. Here are some major reviewers comment that we got after D3. So heat rejection issue into the room. So initially it was intentional to not fit a duct or not remove the heat from the room to measure the extent of the rise in the temperature when the heat was rejected into the room to see the effect of natural ventilation. But later a flexible duct was attached and heat was rejected out of the room. Next, we are answering the further comments in next PPTs. So in this table, we can see that we have thoroughly compared our product with market available solutions, a 1-ton split AC and a ceiling fan. We have considered 8 hours operation of all the appliances, and we are considering 8 rupees cost for 1 unit of electricity. So we can see that the monthly cost of our product is 960 rupees, which is significantly less than a 1-ton split air conditioner. We have also highlighted the parameters where our product is performing better than a 1-ton AC. These parameters are our product is able to provide thermal comfort. It is portable, it is easy to install and DIY friendly. It works along with natural ventilation as well. Next, an innovation means nothing if it's not affordable. So let's move on to the pricing of our model. We have employed Van Westendorf price sensitivity meter, where we surveyed around 40 participants from various age groups and working professional and studying demographics. We asked the users to provide us 4 prices which are too cheap, good value, expensive but affordable, and too expensive. So based on the data that we get from our users, we were able to come up to point of marginal cheapness, which was around 5,500 rupees, point of marginal expensive, which was around 24,500 rupees, and an optimal acceptable customer price, which was around 14,999. Our customers provide us value, and cost will provide us the business. So moving on, we have considered a production of 100 units, and after breaking all the prices for the components and market expenses, our final cost stand up to rupees 8,880. Now we have a profitable product. Our next step is bringing it to the right customers through right channels and through right marketing strategies. So in marketing strategy, we had a comment that the COGS does not include the market margin, and after this we have changed our marketing strategy. We now have a 2-phase marketing strategy, where in the phase 1 we will adapt to D2C model and a hyper localized marketing. In this phase we have a margin of around 24% and retained profit of rupees 3,000 for per unit sold. Next, in the phase 2, we plan to scale our business and scale our business to retail and e-commerce, where the addition of extra channels will reduce our margins to 12% and will yield to 15% retained profit. Next, based on the comments, we have also calculated the simple payback period. So for a user switching from a 1-ton split air conditioner to our product, the simple payback period was just under 1 year. Now, so far we have seen the economic and technical aspects of our product. However, it is also important to see the environmental impact of our product. So our products align with 3 SDGs, SDG 7, SDG 9 and SDG 13. Target 7.3 focuses on the improvement of energy efficiency. So our product is 62% more efficient compared to a 1-ton split AC. Next, target 9.4, which focuses on the improvement of infrastructure and low carbon infrastructure. So our solution is able to save around 100 kg of CO2 emission per year. And next is target 13.2. So after saving energy and reducing the carbon emission, our product also supports the pathway to limit the global warming to 1.5 degree Celsius. To understand the holistic effect of our product on the climate, we also did a life cycle analysis after considering a 10-year service life of our product. In this life cycle analysis, we were able to we understood that more than 95% of the CO2 emitted was because of the use phase, out of which the operational energy CO2 emission due to the operational energy was the highest, and the refrigerant leak was the second highest. Our product saves around 10,000 kg of CO2 in its life cycle, which in perspective is equivalent to the CO2 absorbed by 500 mature trees within a year. Next, we will move on to the commercialization. So we have we have made a strategy for 1 year and divided the 1 year strategy in 4 parts, in 4 phases. So in the first 3 months, we plan to secure the design for manufacturing and IP for our product. In the phase 2, we plan to manufacture and sell 10 alpha units and also integrate IoT with our device. In the next phase 3 and phase 4, we plan to get pre-booking orders and deploy 100 pilot units. So the major part of our incubation money will go into R&D and making our product better. We expect support from Sign Incubation Center, which is in IIT Bombay, and IGBC and Griha. Our team majorly focuses on the commercialization part, operations, and R&D. We also have expert supports from HVAC and sustainability.
Yeah. So to conclude with what our product offers is actually a paradigm shift in the residential cooling market. We offer affordable portable thermal comfort at a fraction of energetic and economic cost. We were able to manage whatever thermal goals we are prescribed prior. We're able to give you thermal comfort within the IMAC or comfort ranges, and also we are able to keep the energy efficiency within the prescribed limit. We have great plans out for our product, especially two which we are focusing on. One in IoT, wherein the product will adaptively measure what is the conditions in the room and also adaptively set the set point at which the cooling water is circulated. In turn, it will make it much more easier for the user to use it. And two, the second major change is that we're going to actually eliminate the water loop. Right now, we had to use a water loop in the system so that to complete the product within 1 year time frame. But once we eliminate the water loop, the product will be much more compact as 40% less than whatever you're seeing here. And also, since you're eliminating that secondary water loop, the heat transfer losses is also losing. So thank you. Yeah, yes, Sanjay told you.
You're done? Okay, fine. Thanks for that, team Shitansh. We'll move on to the Q&A session by the jury. I'll start with Yash is ready. Let's go.
The product is working right now.
Yes.
Can I experience it?
Yes.
Yes.
It's ideally not meant for this air conditioned rooms though. Water is at 24 right now. So
That's giving the major airflow.
yeah, that's conductive part. The radiative part you will feel.
Ma'am, please, there is a
Ma'am,
fan.
ma'am.
Ma'am, there is a fan inside, so please.
Can you adjust the height and show?
Yeah, we can show.
Can
No,
we
one minute.
can we first
One
turn?
minute. Oh, hey, please,
Yeah.
please be careful.
Yeah.
there.
For that,
We have to consider that in the next section wherein we'll be able to put something above. Adjust karna. Adjust karo.
this can go up to this
Yeah,
height.
but right
and
now
when
we already
person is
decided.
sitting, we can lower down.
No, right now it's like only kept within this range, so sitting and standing, that's all. Look at that, look at that. Good look. Look there, no, look there.
I'm just sure. Yeah. Don't just leave it.
Itna kafi hai?
So up, I was talking, thank you.
Where is the exhaust duct?
No, right now we are not put here, but it's gonna it's
And
connected.
for this part, moving part. And one more thing that this is moving part, so we are thinking that so yeah, so right now this is moving mechanically. The height is adjusted mechanically, but we are thinking that the warm wheel and warm wheel motor gear should be will be installed so that in a one click you can raise and lower the dome.
Yeah.
Maybe move it
Yeah,
up. Is it
yeah,
okay?
ma'am. Yeah, just a bit. You're okay with this?
So
Be careful when you
kind
get.
of yeah, I'll be careful.
Where is the water getting exhausted from?
Yeah. It's going
Oh,
Yeah.
from here.
Be careful when you touch it. Right now, it's not completely inside.
This part is supposed to be cooler.
Yeah.
The
That's
inner
aluminum
dome.
dome.
Yeah.
Dome, yeah.
We also thought of using
Be
copper,
careful
but
when
it will be
you
weight.
it might leak only, so be careful when you tell them.
Yeah.
What temperature will
Right now it's just 24, but
the surface temperature comes around 22 when we set the
Water
water temperature
temperature.
around
ma'am,
20.
please. Oh, okay. Yeah, it's not meant for.
So
It's
yeah,
still test.
so it is in testing phase.
Okay. Oh, that's what.
Okay, because I will move up.
Yeah.
Okay. A couple of questions. Is the temperature controllable in this unit?
Right now it's manually controllable, but future ahead will be
Like
have to
just
be
like an
controlled.
AC.
Yeah, right now it's like.
Okay. Which charging plug are you going to use? 6 amps or 16 amps for this product?
So right now the charging plug is 16 ampere because of the compressor.
Is it possible to bring it down to 6 amps?
So we have not used a custom compressor. The compressor is a market available compressor, but if we are customizing the compressor, yes, we can bring it down to 6 amperes as well.
Because in your hostel itself, are you going to find a 16 amp plug?
No, actually.
Socket?
No.
You are not going. I really like the depth you have gone to, understanding the psychological effect. Even though it's cooling only some parts of the body, you will feel a lot cooler. And I'm happy that you have tried to address the exhaust issue, but we need more depth over there. When the exhaust duct is there, will this product be as movable or as user friendly as it is right now?
Can you do that? Okay. So we had actually looked at multiple options for the exhaust issue. We tried water, which is a good source, but that's not good enough for us. So yeah, I understand the question. It might not be always the best case, but we are trying to keep it as flexible and as small as of an exhaust, so that see, like a portable AC, if you see, people also have the same exhaust issue with the portable AC. If we are able to bring it down as simple, as small as that, that's still comparable to what is available in the market. That's the best solution we have right now.
Okay. And last question, you said that your current margin is about 24-25%.
Yes.
And then once you launch it on marketplaces, it will be 12%. Is this sustainable? Will you be able to make this company survive with 12% margin?
So when we are saying that our margin will reduce, we are assuming or considering that the number of units sold
The
will
volume
increase.
will be
Yeah.
very high. Typically, any consumer appliances company cannot operate below 30-35% margin. You have salaries to pay, you have several other operating expenses, and this is the gross margin I'm referring to. So think about that, and then what will be the price of your product if you are keeping 35% margin?
Sir, I have one more thing to say that during the brainstorming during marketing strategy, we also came up with a strategy that we didn't mention in the slide, which is renting our product to students, and then we are only managing or servicing. It is a rent-based.
The business model changes.
Yeah,
That that can maybe be an interesting thing.
Very good, very innovative, and very happy to see a working model. Very well done. And I, as Yes said, I was very happy to see that you considered the differences in temperature from different parts of the body and where heat gets generated. One question, you said you are able to reach IMAC comfort limits, IMAC R comfort limits. At what ambient temperatures are you able to reach that?
So most of our testing, most of our testing has happened in the last month of May and month of June, which has been the second highest temperature months in Mumbai. Usually the ambient used to vary from somewhere around like 36 to 38, 39. That's the ambient temperature. Ambient as outside. Whatever ambient we measured is inside the room, whatever
Correct.
shown in the graph.
So the inside the room you are measuring around 32 or less, actually 30 is what you're measuring
Like
inside the room.
it came around like 30 to 32 range, yes.
So how are you able to maintain at 30 to 32 when the outside is 38?
So that particular building has a very big thermal mass.
Because of that,
Yes.
because of the building itself.
Yes.
So let's say the ambient is higher and the humidity is higher, then have you considered the risk of condensation?
Yeah.
Yes, yes. So in this dome structure, there is a bottom part which is a water channel. So the it is designed such that the water is collected from the top part, also from the bottom part. So it can also collect the condensed part also.
Okay.
Yeah,
All right.
ma'am, to add on to that, we also considered the design such a way that it aligns with the Coanda effect. So water is easier to flow into that particular channel rather than dripping downside.
Okay, got it. You said in your graph it showed an operative temperature drop of 1.5 degrees centigrade. Is
Yes.
that right?
Yes.
So if the temperature is much more, I mean, is it possible to achieve a lower, better temperature graph? And in your report, you gave a 0.67 reduction in radiant temperature.
No, that 0.67 was considered because there is one room on the other side and the other. So right now the comparison is between if I'm in the room,
Mhm.
the temperature is measured under the dome and
Mhm.
temperature is measured one another point of the room. So to highlight the microclimatic difference.
Okay.
Earlier, when we compared within a different room, the ambient temperature in the room itself was a bit higher by say 1 degree Celsius
Mhm.
different. So which is why the difference was there of 0.67.
Okay, so that was not the right
That was not the right comparison
Right
to modified it rather than inside here and in the different part of the room.
So thank you very much for answering the questions we raised in our D3 comments.
Thank you.
Yeah, good. Very good.
Thank you. Thank you.
Good job, team. I don't really have any questions, but I enjoyed reading your report. Likewise, good presentation, I must say. Very clear definition on who your target audience is, target group is. Liked your approach about personalized cooling versus cooling the entire room. One point, why water? Did you all think about anything else?
For the refrigeration?
Yeah.
Yeah. So right now we have only used water, like I mentioned in the last concluding, that within the time frame of 1 year where we started the ideation and finishing presenting here, if we had considered something like a normal refrigerant or something else, we might not have able to finish it. But we had a much more say confidence in finishing with water. But we do plan to remove the water out of the system so that it will help me make us even more compact.
Okay. I think it's a great idea that you'll have come up with. Think of extending it in the other direction, which is like a personalized heating for north of India. A similar thing could actually work. So while there's one side is cooling, the other side is heating as well.
That was actually one of our ideas which we had.
And good job, team. Good job.
Okay. Thank you. Thank you for it.
Thank you, jury members. Thank you, team. Great presentation. So we're going to take a 5-minute break and we'll come back with the fourth team. Okay, so it's time for our fourth presentation in the RCR division. Uh, the fourth presentation is by Team Gharkul, and the name of their product is Melon Cool. So that sounds very sweet. It can be a modular wall insulation panel and a window curtain system built using sustainable materials to reduce heat gain. So Team Gharkul, could you please take the stage?
All right. Hello, everyone.
No,
This is Team Kharkul.
just 1 second. Yeah. So you have 20 minutes to present your presentation to the jury. At 15 minutes, I will ring a single bell so that you know that you have 5 minutes left. You have a timer visible here. So you have to finish within 20 minutes. If you don't do it, I will stop the presentation. Okay. And after that, we have a 10-minute Q&A session with the jury. Right. Okay. Good luck. And Team Gharkul, your time starts now.
Hello, everyone. This is Team Gharkul, and we are here to present you our prototype, Melancholic Fits. In short, Melanchool. Our team is consistent of aerospace engineers, electrical engineers, electronic engineers, material engineers, and civil engineers. So sometimes the solution to a problem comes while looking at another problem. And this problem became one of our resources. The problem that I'm talking about is the stubble burning, agricultural waste burning problem. Every year, around 35 million tons of parali is burned by our Indian farmers in the region of Delhi NCR, in Haryana and Punjab, which causes the increased AQI during the winter season, and again, which causes a lot of health issues we see in the news all the time. This burning releases particulate matter of around 2.5 and 10, the size of particulate matter 2.5 and 10, oxides of carbon, nitrogen, sulfur, and very toxic carcinogenic gases. This is a problem for humans, animals, and the ecosystem. The problem statement that we were given, the heating crisis, the increased temperature that we are looking around, the heat waves that we are seeing, according to the India Climate Action Plan, sustainability and energy efficiency is the way to build resilient buildings. Using these things that we found out, we made them our core values: sustainability and energy efficiency. So, how can this problem be the solution to a way completely different problem? To understand this, we have to understand the science of straw. Straw, parali, stubble, any straw, it has four major components: cellulose, hemicellulose, lignin, and silica. Cellulose and the hemicellulose form the structural part of the straw. They give the flexibility, they give the structural strength, they are fibrous. This is what is basically the curtains that we use, the cotton curtains. You extract the cellulose, and that what is the major structure in the curtains. It is fibrous, it provides micropores, which creates the air envelope, which will be explained later. Lignin, it is a thermally stable compound. I want you to make sure to remember the application, the adhesives, which will be very relevant later. And silica, we are very well aware of uses of silica. Parali can not only be used like by getting out the components and using it differently. Overall, it can be a very good substitution for packaging material. It can be used in building materials. It can also be used to make sustainable handmade utensils. So we'll move on to the solution part, how we came up with the solution.
Okay, with the understanding of science and the application of Parali, so we'll move to the what exactly the solution will be to cater our problem. Solutions are derived from the intentions and the value that it will provide to the globe. So here our intention is to lead a sustainable future with helping our farmers and the society. So while building the approach to how to link our problem with the solution, we looked around and observed the things that we face. So here we come up the users. What kind of user we have, and what are the problems, challenges, and the need they require for that. So as according to from our experience, we are as hostels and rental tenants. Our challenges mainly are temporary accommodations and small living spaces. While what actually we need is a portable cooling system which can be easily installed. Another user can be an apartment resident which is living in a concrete trapped heat buildings. Also they cannot modify their building structures, and what actually they need is a retrofit cooling solution which can be a lightweight installation because they don't need much heavy stuff. And another user can be a urban middle income family. So with what are their challenges are like rising summer temperature, high electricity bills, and a limited budget for major renovations. What actually they need an affordable cooling solution which is easy to maintain. Now, compiling all those constraints, what actually our material, our product should hold these qualities. It should be a low cost material. It should be durable. It should have low maintenance. It should have retrofit ready thing, and it should be a lightweight with effective cooling. Now, concluding all the things that are required in our product and what are the alternatives that can sustain those constraints, we all compile all the things that are available in the market and that can be researched on. And compiling all these things, we can directly link our solution with the Parali solution that is affordable, that is local, that is sustainable, and that is very retrofit friendly. And the most important thing, address the Parali burning problem. Now we come up with a solution that is melancholic fits. The melancholic fits are the curtains made up of parali with a lot of iterations and lot of manufacturing work has been done over it. And how does it work? It works by uh, influencing the transfer of heat, which is majorly by the sun, that is by conduction, convection, and radiation. How it works? It works on the basic concept of the manufacturing of the whole curtain part and the properties of parali, which makes it more porous with air pockets inside that help to trap the moisture outside and make it more comfortable and thermal comfort living. And how it is made? So making parali curtains is an iterative process. We had done a lot of changes. We have a lot of sampling in that particular process, starting with the grinding of parali. And there are like different kind of parali. Like we do have rice husk, we do have wheat husk. So there is difference between those paralis also. And we have also tested on both the samples too. So here we have grinding of parali and plate printing. Like we need a mold, skeleton kind of thing. So for that we 3D printed a plate model. Then we had done a sample preparation. So here comes the thing that is very important. That is the binders. Here parali is not only binded by some few binders. There is special kind of thing, and we were not aware of those binders. So we learned about that. We went to our chemistry department and explored what are the binders available for us. So here we concluded with some basic binders which are related, which research are going on related to those binders, that are latex, guargum, lignosulfonate, and methi dana. Actually, methi dana is a fenugreek powder. So it's the binding property is very good for that. And each sample shows some different property to us. Like some are providing very good strength and some are providing very good temperature drop. So here we will, it was all molded and then went for tested. Now the iteration process that we had done, all these samples are being prepared here. And we went to the iteration part that concludes what are the things which we went through. Like it also concluded with the batch rejection. Actually, we had a lot of sampling thing we went for us, and that was the batch rejection was around 40 to 50% because a lot of samples were with us, and we narrowed down to a composition of those samples which actually make us an optimized version of curtain. Now let's go for validation part.
Now, to validate our solution, we initially considered multiple KPI factors, but since our primary goal was to focus on the thermal comfort, we narrowed down the evaluation to two key factors, which were the temperature reduction and the absolute humidity. So, to consider to conduct the validation part, The process was of 3 stages. The first was the exploration of the binders. The second was the miniature box testing, followed by the real room testing. For the exploration of binders, we initially started with different natural binders, combined them with the parali, and then made the samples. The different samples were then tested. The different samples were then tested on the basis of their mechanical properties, like considering their structural strength, their flexibility, and their physical appearance, along with the thermal parameters, that were the temperature reduction and the humidity retention they offered. Followed by the next stage was the miniature box testing, wherein we created a mini room setup. We used a halogen bulb which acted as a heat source, and it to replicate the or to simulate the heating conditions. In this, we tested all the samples and calculated we measured the temperature difference and the humidity retention they offered. And upon that data, we compared the different we got 2 different charts for humidity and for temperature. And based on that, we narrowed down our final materials. Now, this was the result of the testing box setup. First was the methidana, the fenugreek powder. It offered very good binding, but it had low to moderate thermal insulation, so it was rejected. Next was natural latex. It had promising results, but during the manufacturing, it had some consistency issues, like it was breaking, and maximum of the batches made from natural latex were rejected during the sampling part. Next was the guar gum. It provided good strength, it provided good bonding, and also strong insulation performance, which made it a preferred choice. Next, after finalizing the product, finalizing the material for our product, we made a full scale prototype for it. And after the prototype was made, we conducted a full room testing for it. We arranged 2 separate rooms and conducted the testing. One room contained the curtain and the other was without the curtain. Both the rooms were tested parallelly across 3 days. Due to some weather conditions and inconsistent weather conditions, we were not able to test it for a longer period of time. So this is the data of the 3 days. The first one is the temperature difference, and the second is the humidity difference across the 3 days. The temperature difference graph shows that the rooms with the curtain across the 3 days had maintained a significantly lower temperature, especially during the peak hours, that is the afternoon period, when the external environment has extreme heat, compared to the other room which was without the curtain, or which it was basically with the normal normal cotton curtains which we have. Second, similarly for the humidity, we got the similar results. The one with the curtain showed more, the room with the cooling curtain showed more stable humidity differences, while the one without the cooling curtain showed a decline, a rapid decline in the humidity across the throughout the days. Based on this result, we concluded that although based on all this back based on all this result, we concluded that our prototype was able to thermally provide thermal comfort, maintaining the temperature reduction, also considering the humidity. The temperature difference we were able to observe of around 5 to 6 degrees Celsius, and for humidity we were able to observe around 10 to 15 degree humidity retention, compared in both the with curtain and without the curtain. So now, where do we stand?
Okay. So now, as we have discussed about what is our product and how we have tested it, we will be discussing about where we stand in the market and how do we position ourselves and how do we see our product impacting the lives of people.
Okay, so discuss first part discussing the beachhead market, which is to target a very narrow segment of the market, because the idea as we have presented is a very niche idea, a very new idea. The parali has many other uses but hasn't been used as an insulator, as a curtain for room. So we are going to target a very narrow segment for the starting period, and these three particular segments which we were deciding to target based on the results of what we got in the testing part. First, we want to target hostel students, because we ourselves are hostel students and we face these heating issues while residing in the hostels every time, every summer. So what we want to do is that we want to reduce the temperature by some amount so that the coolers and fans can be effective for students, and the solution has to be budget optimal, because the hostelers mostly have some budget constraints, and that since that is a temporary accommodation, the solution also needs to be portable enough. Solution also needs to be lightweight, and it also needs to be uh, uh, compatible with that window size, with that size of the room. And then we have the renters who cannot renovate and uh, who cannot change the major things in their home. And then we have the apartment residents who reside in the concrete buildings and they suffer with the indoor heat buildup. And most of the problem that apartment renters have is the high AC bills. What we are aiming to do is that we want to reduce that bill using some passive cooling mechanism. We also have a tagline for our product, that is passive cooling that cools both your room and your electricity bill. By which we mean that we want to delay the peak hour when we need to, on our ACs. Uh, if I compare with the alternatives for cooling that we have, the AC, we are not claiming to replace it. It will be here, but we are aiming to reduce those electricity bills by reducing the electricity usage, by reducing the duration for which the electricity is consumed by AC. And cooler, it performs poorly in the humid climates. Looking at the smart window film and structural renovation is not feasible for renters. And smart window film, these are majorly the expensive products, and the middle class is not able to afford them. Okay, now after defining our target customers, how do we reach them? We are looking forward to three ways to reach our customers, which is first will be we have divided them into two parts, which is the consideration objective and the conversion objective. We want to use digital marketing, which is social media, and telling stories about the actual energy savings and sustainability campaigns through social media. This is for consideration objective, that is to reach the customers, to spread awareness about the product. And then these two, the demo marketing and the society cooling drives, these we are looking forward for the conversion objective. We want to do demo marketing like live installations, pilot testing in the homes, and before and after comparisons, looking forward to convert more customers. And for the society cooling drives, we want to collaborate with the housing societies and apartment complexes so that we can reach out to whole of the community at once. After that, we want to who can be our partners. We want to partner with businesses in such a way that gives us more of a widespread business scope and widespread customer base also. The government can be our partner because government has housing schemes, government schools also built up, but all of these apartments and schools and rooms do not have ACs and do not have fans. They at least need the indoor temperature to be reduced by some amount so that at least the fan can be effective. So in that case, when the government is constructing those houses, we can collaborate with them and they can use these curtains in those houses. And with the industry also, the vision with partnering with the industry is that we can partner with their CSR initiatives. For example, as we have seen recently that whenever we take a flight with Air India, they provide us a card with some seeds embedded into it. And if we throw that card somewhere, that is a CSR initiative to plant more trees. We can partner with such CSR initiatives to boost this sustainability. Like to they can help us sell the product to the employee, or we can advertise us through they can advertise us through their CSR initiatives. We want to market ourselves in such a way that we want to appeal to the emotional aspect that is related with the sustainability, because every year whenever the global warming news comes or whenever the temperature rises, we are looking forward to that. And the distribution partners, hardware stores, building materials, interior designers, architects, and all of these can be looking forward to scaling. We want to define 3 stages here, which is the direct sales, which will be before this. There will also be a pre-sales stage, which will be the pilot testing and the detailed user testing, because this product needs at least 2 years for a detailed user testing, so that we can know what are the impacts in the longer term. And after that, we can directly sell it to the consumers, the end users. And then B2B sales, we can partner with the industries, we can partner with the housing societies, builders, PGs and hostels, and also with the CSR initiatives. And at last, what we are looking forward to do is we want to make a 100% bio-based binder, which we can license to the other corporations, other companies. Those are the pilot cities which we are targeting first, and those are the reasons why we are targeting them, because extreme summer temperatures and a composite kind of climate, and we have tested our product in the composite kind of climate only. So that was all about.
Great presentation. Slightly out of time there, but that's fine. You are wrapping up. So let's move on to the.
Can we see the prototype?
Yeah.
We
Please,
actually
please.
wanted to.
Amarut didn't allow you, know.
You can come in. You can come in. Jury members, if you can speak on the mic, that would be great. Thank you. Or the participant, just hold it to him.
Painted like for aesthetics.
Yeah.
So that's the material, and you've covered it with a cloth.
Yeah, it is the muslin cloth. Actually, muslin cloth is also known for its thermal comfort. So we are like a hybrid version of things.
Yeah, it is.
The smell is.
Yes, we wanted it.
To coat it with essential oils to kill that smell.
How long do the oils last?
The oils will last longer. Actually, we wanted it to be a bit more natural, so that it's a bit more honest compared to the.
And the oils will be using the during the preparation. Like it will be mixed.
It will be embedded in, so that won't be an issue.
Yeah, actually, we are in the research phase, like for
We are in the research
more
phase
and
for
more
that,
things can be done over a period of time. So we can work on that too.
This the.
Yes.
Yeah, this one.
Okay, so these are not
Shade.
retractable.
These are not retractive. These are like vertical strips.
Interesting. Like
that
we
turn.
have to need some sunlight there, so we can twist it a little.
Thank you, team, for the presentation. I think it's a good exploration of material and how you're experimenting with it and inspired by local environment. So I think good job on that. I think that needs a lot more exploration and testing and research. I think you've done a good job in the last 7 months when you started the competition to where you are today. So there's a bit of a challenge with this. How would you manage opacity, translucency, right, which the traditional curtains do offer?
Using this feature that these strips do turn like this whenever we need
That's
some
like the
sunlight.
traditional Venetian blinds.
Yeah. Which one do I need to pull?
No, I get that. You don't need to.
We can do that.
Okay. And what are the challenges y'all are facing when making a full-scale prototype?
Okay, the main challenge that we are facing is the binder thing. We want to look forward to 100% bio-based binder, which is also uh, recyclable, which is also biodegradable, and also provides a strength and flexibility to the curtains. Because right now these are not that flexible. We want the strips to be flexible enough. So for that, what we are doing is we are experimenting by mixing different compositions of those binders that we mentioned, and we are searching for other options as well. So that is the main challenge we are facing here.
So this is the biggest prototype that you've done till date?
Yes.
And this is what you tested at user's place?
The the room that we used for testing, it was the size of 10 by 12 feet, and the window that we were given was around 80 into 40 centimeters. So that was the prototype that we built. It was this one, and it can be folded like this. No. See that.
So whatever you've written in the report or what you presented today is based on this prototype
Yes.
in that room?
Yes.
Okay. Okay, thanks.
I think your exploration on material and development is very good. Excellent work on that. And I'm sure there's more you can do on it to improve it. I have questions on how you are applying or using that material, right? You've chosen to use it as a blind and you've done some testing. So when you tested it, you seem to have tested it comparing a room without any blinds with a blind.
Oh, that was the review that we got in D3, right? So the testing results that we showed today, it was done with a market bought a cotton curtain. One room was with the cotton curtain, one room was with the blinds that we
With the
made.
blind
Yes.
that you have
So we
got.
changed the baseline as it was given in the
It
review.
was so you have changed the baseline.
Yes,
And
we
what is
did.
the result that you have managed to get with that? So when you calculated or measured it, so that's what you with curtain and without curtain. What do
The
you mean?
without curtain one is with the store-bought curtains that we had, and with curtain, the curtain that we are referring to is the curtain that we made.
So what kind of a curtain is that? What is the comparative curtain? Because curtains can be many kinds.
You can say it was mostly a very cheap kind of like a synthetic cotton blend kind of a curtain.
So you need to be clear about what it compares to, right? So that is one thing I have got. What about, did you consider, you've seemed to have considered the indoor temperature variation. Now, I can't really read the numbers very clearly because you've got too many colors there, right? What is it that you notice? What is the temperature reduction you're getting? 2 degrees.
When it starts with around 2 degrees, but by the end of the day, when the heat is actually at its peak, we are seeing that it works pretty well. It gives around 3 to 4 degree temperature on a normal day, and on a rainy day, we have noticed that the humidity was pretty low inside the room compared to outside.
So where is the window? Which orientation? Was
Okay,
there a chajja? Was there shading? Was there direct sun? What was the ambient temperature?
It was a west-facing window. The direct sun was on the opposite side, on the opposite wall, and it was pretty clear. There was just ground in front of the window, so
Okay,
there was
so
no
was
shading.
there a chajja on the window?
No, there was no
There
structure.
was no chajja on the
No.
window, so this was the only shading it was getting.
Yes.
So how do you come? So this one is basically you're cutting down the airflow with this, in a way, because if you want to completely get the maximum benefit, the benefit from Venetian is not going to be the same as the benefit from a solid blend that you've got there.
Okay.
It'll be very varied, very different, right? So that's so you need to put that in. What was this? Did you manage to measure the surface temperature of this outside versus inside and the curtain outside versus inside? So that exactly will give you the impact of the curtain of this material.
That surface testing was the part of the box test that we did for material selection.
Yeah.
We
measure this material surface temperature inside the box and just outside the box, and it gave pretty ideal cases like 5 degree, 4.3 degree, 3.8, not a lot of variation with the binders that we used.
Okay.
And based on the variation that we got, we chose the final binder, which was the
Final
quad
binder you can. Okay. Now, what about the longevity? Have you considered maintenance, cleaning, fungal growth, degradation?
because the binders that we are currently using, we don't think there will be a fungal growth problem here. The major problem which we are still working on is the protection from water resistivity, because it's again fibers that you have seen right now. If you add water to it, it's pretty much destroyed. So that's the next step. And the longevity, because again it's parali. If we just throw parali in the sun, in the rain, and keep it just like that, it will last around 8 to 9 months. With binders we can extend that life to probably 2 years, on ideal case 3 years. So it's kind of a temporary solution.
Okay, okay, understand. See, your material is great. Maybe you can look at how you can work with different types of curtains. Maybe you can do a porous jali kind of thicker jali kind of
We
a.
actually have a lot of forms for it planned
Correct.
that
I
would
think
be done in the next 1 year.
I think
for-
it's better than using it as a solid blind.
Yes.
Use it as a maybe a very fine mesh or a jali.
Another idea that we had was like a wall mount. We can make a lot of intricate designs that will look good also, and that also provide cooling. So
So
we had
do
a lot
not consider when you're looking at thermal conductivity, be very careful.
Okay.
It cannot be measured like this. And you will not be able to get what you're given here with this material with that thickness.
Okay.
So be careful with those numbers.
Yes, we'll take care of that. Thank you.
Okay. I'll agree with the comments on material research. Good work there. And I'll also say that this has potential. Please pursue this further, and this can become a marketable product. Another thing I'd like to call out, the presentation was refreshing. It did not feel like I'm reading the report again. So
Thank you.
that's
That
nicely
was the
done.
plan actually.
Yeah. Have you explored the curtain market in general? Because see, this is a product that has so much variability. Every home has different sizes, different types of mechanisms, etc. Have you explored what is the market distribution? Which kind of curtains should you address first? What should be the ideal dimensions, etc.?
Sir, for that, we have seen like those standard curtains that sell in the market, that someone goes and says, okay, I want to buy a 7 feet door curtain, and they buy it. Kind of that.
So are there any standards, 7 feet, 9 feet?
Yeah, a 5 feet is for windows, and a 7 feet for door, and a 9 feet is the long door curtain.
So have you identified what you want to target first?
We want to target the windows that face the sun first, and then we want to target the balconies, the balcony doors.
Okay.
For that, mostly people use the 9 feet curtain.
Will you be able to manufacture for 9 feet with your current material?
This can be manufactured for the 9 feet with the strips idea, but we are skeptical with that whole solid plate kind of idea. But yeah, this one can be done.
Like we can accumulate all these slots and compile it in a similar fashion like that we had done over here. Like that.
Okay. Okay. And can I go? Yeah. I did not see any numbers in your report. Pricing of the product, what is the raw material cost, etc.
Okay, so regarding the raw materials and the pricing, for now, since we had to research with the binders and the materials, for now we were getting it around 1,000 per curtain.
And
The manufacturing cost.
How does it compare to your traditional curtains?
The traditional curtains are around, what I've seen is around 400 or 500 rupees. This is the average price. They can go up also. There are also some 200 or 300 rupees curtain also. So I'm taking an average there. So talking about the cost, the traditional curtains, for what I am taking 400 to 500 rupees cost, they do not give that much of the thermal insulation. But this curtain gives thermal insulation better than those. Other than that, this also gives a ventilation because we have manufactured it in a slotted form. And after, if we try to manufacture it in a bulk way, so if we buy the binders in bulk, because right now we sourced it from like the stores which sell some scientific components or some chemicals or sort of things, so that is why it costed us higher. So if once we reach the economies of scale there, we have also we are also predicting that this can be brought down to 400 to 450 rupees per curtain.
Okay. Okay. Thank you.
Compare Venetian blinds to Venetian blinds, solid curtains to solid curtains. You cannot compare a solid curtain to a Venetian blind, both in terms of cost and performance. Right? Okay. So that's how you have to do your testing. Otherwise, the product has a lot of potential. Please go ahead and do more.
Yeah. Thank you so much.
Thank you, team. Thank you, jury members. Right. So, not at this time. After this, yeah. Thanks. So we are going to take a long break for lunch. We'll start the next presentation for Team Sujanyam by 2:15. So by 2:15, please be back here. Sorry, we'll start at 2:30. So please be back here by 2:15. Folks online, I request you to tune back to this channel and ready for the presentations of the upcoming teams. So we're breaking for lunch now.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world's so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. rolling so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world's so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through.
Hello, everybody. Welcome back to the Residential Cooling Retrofit Division presentations at the SDI Finals 2026. We'll quickly go on to our fifth presentation, which is from Team Shrujanyam. Their product is called Atom Sync. It's a product that combines passive night purge ventilation with active refrigerant-assisted cooling. Team Shrujanyam, could you please take the stage? Yeah. So team, you have 20 minutes to present your work to the jury. At 15 minutes, I will ring a bell once to indicate that you have 5 minutes left. After which, after the 5 minutes, you will not have a 21st minute. Okay. So I will force you to stop the presentation. Post presentation, you have a 10-minute Q&A session with the jury. All right. Is that clear?
Yes.
All right. And Team Shujanim, your time starts now.
Good afternoon, jurors. This is Team Srijanyam. We are representing Nitte University, and here we are to present our product, Atmosync. The first thing that comes is the relevance of RCR product division in an actual Indian market. So the question is, why is this AC demand rise increasing? So some of the factors are global warming, rapid urbanization, growing population, improved living standards, and increased time spent indoors. Just when we also went through some studies that were based on the number of increasing demand of the cooling solutions or the ACs in the market, as well as whether India can actually cool down without heating up. So the target market, we mainly focused on warm and humid climatic conditions. The reason is that we felt that there was no such product which actually catered to temperature, humidity simultaneously, and we wanted a need to find out. So mainly these fall under the coastal regions of India, and our user groups are the middle class and the upper middle class families in residential spaces. Our prime location is Mangalore, which falls under the warm and humid climatic condition according to ECBC, where the average temperature is around 27 degrees Celsius, an annual rainfall of 3,500 to 4,000 mm, and an humidity of 70 to 90%. This also helps us in having a night purge ventilation aspect in our product. So an analysis of the existing cooling solutions. So when we went through the users, we realized that in the market, generally the air conditioners, fans, and air coolers are the most prominent cooling solutions existing. And there was this study that was based on the production and the rise in the production demand over the years. The next, we followed a mixed method user testing where we interviewed 20 people in person and also had 45 online responses just to understand the user pain points, their expectations, and what were the problems that they felt were there in the existing cooling solutions. So the major takeaways were under 4 classifications, which is thermal comfort, energy consumption, cost effectiveness, and user experience. So the flowchart here is actually the user testing methodology that we followed. The stakeholders who were and will be involved are residents, mechanical team, designers, electronics team, computer team, industrial experts, and investors. So now coming more into the user testing aspect, this was an age group of 55 to 70 years. They mentioned about their problems and their needs were they wanted an integration of smart technology with low energy consuming devices. The challenges that they felt they faced were that the process of installation was too hard, and also that they struggled a lot to find the remote for the ACs, and also wanted a product which actually consumed lesser energies. The next age groups were 25 to 55 years, where they mention about their needs and desires, and they wanted fixed active cooling systems and an integration of app control. The challenges that they felt they faced were that a conventional AC actually requires a drilling in the
a drilling of hole in the wall to fix to have the fixtures, and also that each one required a different comfort zone, and it was very difficult to change the modes. And also they didn't want a standalone product, as they felt that the kids would be running in their homes, causing a hassle in the spaces. So overall, whatever user expectations we felt were thermal comfort, humidity control, energy efficiency, smart automation, individual needs, fresh air supply, saving money, easy installation, quiet operation, and good design.
So, taking into considerations all of these experiences of the users, we have come up with a solution to their problems. That is AtmoSync, a smart, sustainable, energy efficient cooling for warm and humid homes. Imagine a cooling system that does more than just lower the temperature. What if it actively creates a healthier, smarter, and more sustainable home? Our main motto is to let nature do the cooling first, and technology only takes over when needed. So here you see the concept for our design. It's primarily based on night purge ventilation, as Mangalore we see has a high diurnal variation in daytime and nighttime temperatures, particularly during the summers. And here you have this opportunity to use this already cooled outdoor air pushed into the indoors and maintaining this lower temperature throughout the day with a compressor system. So this is a look at our product. So our product majorly consists of four regions. One is the compressor and the condenser region here. We have our brains, which is the SMPS and sensor modules here. We have the evaporator and the fans to distribute the cool air throughout the room. We have hygroscopic panels and night purge ventilation section here, and an origami extender. So the primary modes that this product runs on is the adaptive mode. So what this mode does is, as you can see later in the app, we'll be showing that when you set this app to your location, what it does is it refers to the IMAC R thermal comfort ranges for that particular zone and automatically adjusts the temperatures accordingly to maintain this comfort level. So the user does not need to actively search for a remote or control to keep changing it. And then we have the eco mode, wherein with the sensors, it automatically detects when the outside is more cooler and it runs these fans to push this outdoor cooler air in, and the turbo mode, which actively runs the compressor for the active cooling. Energy wise, this is the most energy intense and this is the most energy effective. So some design considerations that were taken into the product design aspect of this was the ledge depth. So when we are mounting this onto a window, you have your standard 230 brick wall. So our product sizing was designed to be within that 230 thickness wall, so you can mount it easily. Then we have the weight distribution, in which the heavier components such as the compressor and the condenser were placed lower, so that it has a lower center of gravity overall and it forms a more stable structure. Then we have our opening height. So windows come in all heights and sizes. So we have this origami extender that can adapt to any height of this window. And we have a weather sealing aspect to insulate the indoors and the outdoors. We have thermal separation between the hot region and the cool region. We have structural feature, that is these columns that are running through are aluminum C channels. And this cavity within the C channels allows us to pass our wiring and the plumbing through that. Then we have moisture reduction, which is a major pain point for users in warm and humid climates. We are trying to incorporate hygroscopic panels to reduce the moisture intake. And we have fans for the good circulation. We have condensate management. So when this refrigerant loop is running, there's a lot of dew formation on the evaporator part of it. So a condensate tray to collect and dispose of the water safely. Clamp for the windows. So a pain point of the user was it is screwed in place. You have to drill holes. So what if this was just as easy as just clamping it to a wall? So a clamp for the bottom and the top, and then aesthetic considerations. So those were all the design considerations. And this was a journey throughout the prototyping phase. Here you can see the different phases. This is the primary structure. Once we've installed the units, the mesh for the airflow, we primarily made this prototype with aluminum C channels and MDF boards covered in varnish so as to moisture protect it. And this is the insulation that we've put for the hot side and the cold side. And this is how our final product looks. Yes. So coming to the testing aspect of it, so what we did was there was two rooms which are of similar sizes, and we had installed data loggers, and this was the data that we've measured. So what happened was this data is not representative of the product because the time duration in which this data was recorded was monsoon time in Mangalore, where the temperatures were already low. So this is not a representative for the whole year because in summers it gets much hotter and the RH during the day also drops. So what we observed was the average indoor temperature over a week, the product maintained it at 2.5 degrees Celsius lower on average and the mean indoor RH. So the hygroscopic panel currently is not as effective in cooling it, but it would be looked in our R&D later on, where some components within the room, such as the plaster of the walls, can adjust for this moisture problem. And then so how is a product fundamentally different from an AC? So an AC has these two units. One is the indoor and the outdoor. Outdoor is pushing the hot air out, cool is pushing the hot cooler in, and a refrigerant running between. But what our system is mounted onto a window with the hot air and cool air here, similar to what an AC is, but our main mode, which is the night purge, which pre-cools the room and offsets the heat spike during the day. That is happening here. And this is also an inlet for the fresh air. So yeah, this data is for monsoons, as I have specified already. Summers, this might form improvements. So what we noticed was in the base case is like the control group for every testing. So every testing, you need to know if the results you've got are actually by the product or from some external factors that you've not accounted for. So we have a base case of a similar sized room in which there was no products running, and our product case in which our product was running. So what we noticed was this provided on average a reduction in enthalpy of around 6.5 kilojoules per kg. So the major modes, the night purge, which is running for 8 hours, consumes so much energy, and the day maintenance for 16 hours consumes so much with the compressors running. And overall, it took around 1.3 kilowatt hour per day. And compared to a conventional AC, we've accounted for a runtime of 4 hours because you don't switch on the AC the whole day. You only use it when you have the most heat load or the demand. So we've assumed a 4 hours. Usually it's longer because people switch it on and then leave it. With this, the enthalpy difference the AC can provide is much higher. So almost 5 times more. But the energy use is much higher than that. So when we see the energy reduction, our product can provide about 1/5 of the cooling for almost 1/10 of the energy use. And since we could not directly calculate the COP, we did a comparative COP of an AC to our product, which comes nearly to 3.2%.
So apart from the cooling functionality of our product, what additional features does it provide? So one is thermal sensation. Atmosync provides good thermal sensation. Then lower energy consumption. As told earlier, Atmosync consumes only 1/10 of the energy consumed by an conventional AC. Next, no outdoor units. Our product comes as a single plug and play unit. Next, easier control. So there can be two ways in this. For people who want manual control of the device, they can use app to control the device. And for people who don't want such overhead, the device comes with default adaptive mode. Next is better aesthetics for house. This product incorporates unique origami designs to improve the aesthetic look of the house and can also be customized as per user needs. So low noise emission. Our product doesn't contain any heavy moving parts, thereby reducing the noise emission. So how can this product be installed? So by the way, these images are AI generated and used only for representation purpose. So yeah, coming to installation, the user buys and gets the product, and he himself can install the product on the window ledge without assistance of any technician. So he will mount it on window ledge and use clamps to adjust it. After installing, he will plug and play the thing, and if he wants, he can control using an app. So let's look at the practical demonstration of installation of our product.
stop falling into portion and be extendable to any window height. Correct reporting.
So looking into the value-based pricing, this is the methodology we followed. So when compared to other devices, cooling devices, so some provide only airflow, some provide only humidity. I mean, some are bad at humid conditions, and some consume a lot of energy. But our product cools, dehumidifies, provides fresh air. It's a single unit, and then we did a willing to pay survey of a pool of 60 people, where 60% of them were willing to pay around 20 to 30K, and 27 were even willing to pay more than that. Then the final pricing, where we came up to 24,000, but to develop this prototype, it costed us 19,000, which includes all the components which are MRP based. And when looking into a bulk order of collection of all the components, the price will drastically reduce. And then for the profit margin, for increasing the profit margin, we are even thinking with respect to the B2B supply. Then we have this hygroscopic replacement, the panel replacements, then the input tax is there. So these kind of aspects are there. And then summing all the value propositions, our product consumes only 0.23 units of energy. Then it saves around 8,000 compared to a 1-ton AC. Then the return of investment is 288% for 10 years. Then the carbon saved is 1,000 kgs. So going through the 5 main features, it is adaptive hybrid cooling system, and it's a plug and play installation. It's app based. Then it includes hygroscopic material for dehumidification, and it works on mainly on night purge ventilation. Then going into the sustainable development, our product's value and its function covers SDG 3, 7, 9, 11, and 13. So for case for incubation, our distribution strategy is that we primarily go with the homes and apartments in the initial stages in order to validate the performance of it. Then we are thinking to collaborate with the HVACs, facade designers, architecture firms, interior firms, in order to implement this product in their design. And then community partnerships like affordable housing, sustainable developers, and etc. like that. Then in the first month, we are concentrating on design and system development. Right now, it's all breadboard and very quick aspect of making the circuit, but we want to later shift to PCBs and etc. Then certification and control testing. Then in finally the pilot deployment and evaluation. So this is a 12-month roadmap where we are going with system design, validation, pilot, testing, and launch. So the total seed capital allocation is 15 lakhs, out of which 40% we have given for research and development, 30% is for manufacturing, 15% goes for pilot deployment and marketing. So this product can even be used in the smaller cabin and office cubicles. Then this is the team This is the team Shrujanyam. This is the product Atmosync, and I would request the jurors to please come forward and go through the UI of the app part.
Is the app that we've developed to control our product, and this is the app that we have developed to which controls the system and working of our product. Yeah. So here you can see the system's up and running. This is currently monitoring the indoor and the outdoor temperatures and RH and indoor CO2 levels as well. So this is the openings for the sensor here. There's the sensor module actively running here, and there's an outdoor module located on the other side. So this is the cooling side of it. So 1 second, I think you will have to turn those on. So it takes about 2 seconds right now for it to relay and then switch on. Yeah, see, it's on. So there's a slight delay in this communication right now, but these you can adjust it as per your
What
need.
changed in turbo mode? You turned on refrigeration cycle.
The compressor will also turn on. But right now, since we've not installed a stabilizer, we've put a time delay so that the compressor does not spoil. Right. And here you can also get readings of your CO2 monitored data. So this is that, and this is your reordering of the filters that we have. And
Why do the clogging happens?
so mostly in this region,
Okay.
this top part. So here the iMac R thing that we mentioned. So under your profile, when you're setting it up, you set up your location. So right now we've set it up for 2 locations, that is Mangalore and Mysore, because we have testing here. So these are the 2 locations that's put in. So if you look at it in the adaptive mode, 1 second. So within the adaptive mode, so these from iMac are, we've set it up. So Mangaluru limits are this, and for our, sorry, Karnataka itself, Mysore limits are so. So this adapts according to the iMac R things, and it sets up. So I think this is turned off.
Future scope.
Future scope. Yeah. So incorporating the entire database would be a part of the future scope.
And with the development of the product in further ways, right? We are thinking to, so right now when it extends, we can see this gap. So right now when this extends, we can see these gaps. No, we can get the table closer. Yeah. So now together. So it extends to the any point of height of the window. At the same time, now the problem with this design is there is gaps, right? There is a leakage of temperature. So we developed a new kind of So developed a new kind of pattern where when a slit of the window is attached to the side, the ceiling is complete. You can see this is a flat surface. At the same time, if you imagine this as a line and pull it, this forms a complete closure. Now this is just zigzag. So this forms a complete seal.
Supposed to incorporate it in this. That's why we had a similar pattern here.
Yeah.
But in time factors.
Adaptive mode.
Yeah.
Not turbo.
So turbo takes 5 minutes for the compressor to start. So we will have that delay because we have not put a stabilizer.
What happens in adaptive mode and eco mode?
So eco mode is majorly for recirculation. So outside, when it's cooler outside, based on the sensors, it automatically pushes the cold air in. And our product is not like your typical AC that cools when the heat demand is high. Ours is pre-cooling it because of the cold air at night from outside, and it's trying to maintain that cool air. So that is how it's very different.
So
So if you switch it on now, it will not work as efficiently. It will start working good from the next day. So this is trying to maintain that good thermal comfort range throughout the day for you, rather than just turning it on when that heat demand is necessary.
What in adaptive mode?
Adaptive mode, like we said, because thermal comfort ranges are different for different places. So based on that adaptive mode, so when someone's setting it up,
iMac range is what you
just fed the adaptive
yes, we've
and
just put the data in right now.
so that
Yes, in within those ranges, yes.
Then it switches between compressor and night purge.
Yes, it does.
our
To
system
maintain in that.
ventilation.
Yes. To maintain in that. Yes.
Without the compressor.
Yes.
So our main is actually the night purge ventilation, which, like you already mentioned, it pre-cools our space, and then the active cooling is like, it's like an add-on which actually
Only when
makes it
necessary.
efficient.
Only when necessary, it's maintaining that coolness. Right. So one thing that we should improve a lot on is the hygroscopic panels, because the moisture reduction is not happening as much as we would expect. So for that, some other incorporation has to be looked into. That is one
So that's
current
one of the
thing
future focuses of what
that
we
should
think.
be. Yes. So here, these sensors are live. If you want, you can test them to check if this is the opening. Yeah. So
So when you test today,
This is the CO2. This one is the temperature and humidity. Same way you have in the back.
so all right now controlled by an ESP32, which is sitting in this section here.
That CO2 sensor actually got spoiled.
No, temperature, whether it's increasing as I'm touching it.
Okay.
27, no, it's increasing.
These sensors are live. These are properly mounted. Anything you would like to ask us?
When you did the testing,
Yes.
was it tested on a natural ventilation?
Oh, yeah. Sure. Sorry.
Okay. So I think based on my understanding, the main USP of your product is night purge ventilation. That's
Correct.
how it differentiates
Yes.
itself from
Which
a
does the cooling first and technology assisted.
okay. Night purge, the name itself says this is primarily meant for the night time when the
Right.
outdoor air is
Right.
cooler than it. Uh, and that is also the time when most of the people want to turn on their ACs.
Right.
So, isn't this product taking away the, or rather asking the user to change their behavior significantly?
Okay, so getting into that aspect of the user behaviors. So right now, even though iMac mentions our comfort range is 27 or 26, we usually prefer it much lower, which is true. We keep it at 21 or maybe even 18. Our product does not have the energy or the capacity to provide that much cooling. Our product is trying to maintain it in a normal comfortable standard which is not too hot not too cold for the user, but what you're saying is correct. It does not provide that additional cooling if a user needs it.
And your compressor is, I think I saw in one of the slides, it's only consuming 130 watts.
Yes.
How is
So
that possible? So,
so currently the compressor we've used, which is running on R134A refrigerant, is a refrigerant compressor, which is not the compressor that we want to put in the final product. So one thing with the R134A is, even though it has almost zero ozone depletion potential, it has a high GWP. So if you want to just change the refrigerant, you have to also change the compressor with it. You can't just change it. So working on that is also part of our future scope, wherein we are trying to put a little better compressor. But for the current one, this is what we're using, and
and with
this is what we're
130
getting.
watt, how much cooling can you expect?
So our compressor cooling is not the main focus of our thing. Our focus is when the outdoors are cooler, it does the cooling
No, so
majorly.
my question
Does
is
this, yes.
from this point that you want to maintain the
Right.
indoor conditions within an iMac band.
Right.
Uh, Based on your current system specifications,
Yes.
will there be outdoor conditions where no matter how much you try, you won't be able to maintain indoor conditions within iMac bands?
There might be conditions like
There,
that.
I think there
In
will be
which
more
case,
such conditions than the favorable scenarios, right?
I don't think so, but we've not done testing for the whole year. Like I've said, the testing that we've done is also for monsoons only, and that too, the 1 week that we did, 6 days were raining in that. Only one day we had good sun. So that is not representative of a product. So we don't know how it will perform throughout the year. That
And
is
can
true.
this be used in a place like Chennai where outdoor goes to say 40 degrees or even more than that?
Outdoors, it depends on the diurnal shift in Chennai car data. So we'll have to check that. If there is a good diurnal variation in Chennai's climate, this is a good option for there. Because see, the thing is with the diurnal variation, when outdoors are cooler, when this air is pumped in, you can always have high thermal mass items in your room that can store this coolness and offset the heat spike during the day. So these can all be incorporated later on. And similarly for the humidity also, it doesn't need to be part of a product. It can be an addition wherein the wall plasters or some materials in the room can do this humidity control as well.
Okay. Final question.
Yes.
Because you have ventilation built into the product, is it safe to assume that at any given point of time, there are pathways for air movement from outdoor to indoor, even if your refrigeration cycle is turned on?
There's definitely a pathway. If there's a wind blowing directly into this, yes. But there is a mesh, there is these hygroscopic panels, and there is a fan. So obviously there will be small leakages happening. Yeah, that is true. Will be there.
What is the flow rate of, what is the test room size that you have tested
So
this on?
yeah, 3 meter by 4 meter.
3 meter, about 12 square meters. And how long did it take to bring down the temperature to whatever 2.5, 3 degrees
So
that you showed?
that was not the time duration of the compressor. So it was after one night. So we installed it on second, third onwards it started running, and that 2 degrees is an average over that week. So we've
So you're-
not done the calculation of how much time it took to cool it down by 2 degrees.
So you have been running it for 24
Yes,
hours.
24 hours it's been
So
running.
constantly. So you're saying that this will have to run all the time.
This would have to run
all the time.
Yes, but
So what
with
is
a small
but what is
yeah,
what is the flow rate of those
fans.
of the
Yes.
fans?
So currently, you want to take that? Or
in night purge cycle, natural ventilation or mechanical ventilation cycle, what is the flow rate that you're getting?
So keeping like an approximate air velocity of 1.25 meter per second in the middle of the room. So when we did a calculation, we realized that the fans that should be placed in the model should at least have a CFM of 156. So in our final model, in our final product, we'll be implementing that. But due to lack of availability of the devices, we used a lower CFM fans. But then, yeah, we have also tested based on the air velocity.
we had given orders for those higher CFM fans, but since it didn't arrive on time, we were forced to use lower CFM here. So the testing was done with the lower CFM fan.
With the lower CFM fan. So what do you think the night cooling, night purge ventilation? So number one, this system would have to run all the time, 24/7.
All the
At
time,
night,
yes,
whether it
given
is
a small
occupied
gaps.
or not.
Yes.
Right?
Yes.
So whereas a standard air conditioner would run only when required.
Correct.
Right? So what is the have you sort of considered that in your energy calculation that
Yes,
this
we
has
have.
to be run?
Yes, we have.
Let's
So-
say over a 1 week time,
Right.
you are running 24/7
Right.
versus an air conditioner might run only for about 6 hours a day.
Yes, that was accounted into. So we did the energy calculations based on that. So we assumed the AC is only running for 6 hours, only when that heat demand was there, and that is, I mean, you can see that in our energy calculations.
So what was the is the cooling similar to this in terms of the TR or the tonnage of that air conditioner
Right.
that you compared the air conditioner? What did you compare that versus this? What is the tonnage?
So we were trying to compare COP of the system. So compared
COP of the system is fine, but what is
Yeah.
the cooling efficiency? How much cooling is this given versus
this,
the air conditioner?
temperature wise, enthalpy wise, this gives you around 6.5 kilojoules per kg of air, and AC can provide around 25. So it is very much less than an AC, the cooling reduction that it can provide. But compared to the energy use, so even though this is running for 24 hours, it still takes much less energy than an AC would take to run just for 4 hours.
But is it able to bring down the room temperature to the same level?
Not as much as an AC, no. That I think we've mentioned, not as much as an AC, but it tries to bring it down to the IMAC referred comfort ranges for people. But people prefer it much lower, 22, 21, 18 also.
No,
some
leave
people.
that aside. I'm just asking whether you're doing a like-to-like comparison. When you are doing a base case versus a product
Right, right.
case, right? Both of them should have a similar cooling potential.
Okay.
Night purge ventilation in high humidity areas is possible only for very small times of the year. Like in summers, the
Right.
night temperatures are much higher than what you want the indoor temperatures to be.
Right.
Diurnal is actually low, not high.
From the historical data that we have, we checked it in Climate Consultant. There was a good diurnal variation for almost 6 to 7 months. So the peak time we had almost 10 degrees drop during 3 to 4 months, which is the peak summer times. The other times we still had a reduction of around 6 degrees for the
Yeah.
other 4 months.
Which
But
is
there is
not
this
considered very high if you compare to
True,
other areas.
it's not
It
very
is
high.
not considered high.
Yes.
So the 10 degrees diurnal variation that you get,
Yes.
it takes at that temperature drop. You're talking about the highest
Right.
during the day and the least
Lowest
during
during
the
the
night.
night,
And the
yes.
whole of the night will not be at that
It will
least
not,
temperature.
yes.
Right?
Yes.
So it's not, the night cooling will probably not work through most of the year because the external temperature, especially during summers, might
Right.
be higher than what you want the internal temperatures to be.
Okay. Right.
right?
It might be a case because we've not tested this
Yeah,
during summer.
especially summers.
Yes,
It
yes.
could probably work in winters
Yes.
as background ventilation,
Hmm.
right? But when night cooling can work, that is when people use bedrooms.
Right.
What is the advantage of this over just opening a window?
So just opening a window, what happens is the next day that room is still getting much hotter. But this tries to maintain that coolness within the room. So at night you don't get up, open the window. There's a lot of problems that come other than just mosquitoes, insects entering your room, maybe rain coming in. So opening window is not always practical for someone who's going to bed. So this maintains your ventilation also, air quality also. So CO2 sensor here also monitors and tries to achieve the recommended air change per hour by NVC. So those are some other aspects of it.
All right, let's agree to disagree on that window part.
Okay, okay. Yes.
I think there's a lot of work to be done. Thanks, team here. There's a significant difference between what was done in a report and what we're seeing in the presentation.
Yes, yes.
There's a marked improvement, I must say that, but there's a significant difference. Is this a prototype that you'll have done in the last few days?
This the last 3 weeks, yes. We did the testing a little late. That's why when the testing was happening, it was during the monsoon. So April 3rd to 9th is that range. So
So I'm assuming you've not
it was much
tested
later.
with any of the users as such.
So we quickly showed them the pictures of it. So that was we've updated the report accordingly and we've given it. So yeah.
Okay. Then one question that I have.
Yes.
What is your learning from the prototype that you have made, and what change would you make to this prototype going ahead for the next iteration?
Right. So some things would be in the extender on top. Right now, we've not designed the clamps. So the clamps would be one aspect. The condensate that forms from this, that is free water just going away. If we could use that also to cool that compressor part, that would be another addition. Finding a higher capacity compressor that can actually achieve the cooling demand that people would require. If someone wants to set it to 18, it can still achieve that. So those would be developments. It might increase the price a little more, almost making it close to an AC. But this at the same time would then account for the RH and the air quality that the conventional AC does not do, which it only reduces temperature.
And just one feedback. I know I've done this in the report as well. I don't know if you had the chance to read through it. But I think somebody at 25 years and somebody at 70 years, their expectation needs are completely different. I
Right.
think try not to generalize it so much. I mean, whom are you designing this for? I don't know if a 70-year wants to use a smart automation app.
Okay, so one thing, we'll clarify on what we meant by smart automation. So the pain point of the user.
Sorry, you don't have to get in specific, but I think what I'm trying to say is that the needs are very different, the lifestyles are very different.
Correct, correct. So
Yeah.
I'll just clarify what we meant by that. Then I think this will be cleared. So what we meant by smart automation is the older people find it hard to use the remote, find it hard to find this remote and use it. So this adaptive mode that automatically sets it to a comfortable range. You don't have to use anything to change this. That smart automation is what we meant by what caters to the older people. So they don't have to find a remote or press or know any of this
Cool.
for this product.
Thanks.
to work. I hope that cleared.
Thanks, jury members. Thank you, team.
Thank you.
That was Team Srijan. We'll be back in 5 minutes for the final team. All right, let's settle down. I'll start calling names of Manoj. Let me know. Yeah. So we're here for the final presentation from the RCR division. This final presentation is from team Collapsible Indian Urban Furniture. So I know the jury members and our team is also, we are very curious to know the origin story of your name. So uh, their product is Cool Chat. It's a lightweight passive rooftop cooling retrofit system. Uh, team Collapsible Indian Urban Furniture. Could you please take the stage? Okay, team, you have 20 minutes to present your work to the jury. You have 20 minutes to present your work to the jury. At 15 minutes, I will ring a single bell to let you know that you have 5 minutes remaining, after which you will not have time to continue presenting. I'll stop you from presenting. At the end of 20 minutes, we have a 10-minute Q&A session with the jury. Okay, right. So your time starts now.
Good afternoon, everyone. Just a clarification for our name. There is no relation with the product. It was decided very at the beginning, but iterations happened and it changed. So, good afternoon, everyone. Um, s- I'd like to start with a simple question. What are the most basic necessities of human life? Food and water, clothing, and shelter. For centuries, shelter has protected us from nature. But what happens when nature becomes so extreme that the shelter itself can handle? Most of us respond by turning on the AC, cooler, or fan, or simply moving to a cooler place. But what about those who cannot? What about the millions of urban families who return home after a long day of work only to find their homes hotter than the outside?
Let me introduce you to Solanki Nanjibai, who's a 52-year-old lemon vendor living in a dense settlement in Ahmedabad. After spending his morning working in the hot streets, he returns home hoping to get some respite from the hot weather. Yet his home remains unbearably hot. As he says, after a full day of work, I just want some comfort at home, but the heat never leaves. Moreover, think about his wife and children who spend most of their daytime in the same house. They are not alone. Their neighbor, Sultana Ben, faces the same challenge. In fact, millions of families across India live under metal sheet roofs. According to the 2011 census, 3.5 million homes have been identified to have metal roofs in these settlements. However, this only accounts for 40% of all informal settlements. If we project to include all informal settlements, there would have been approximately 5.4 million such homes as of 2011. It is important to note that these numbers are outdated and highly undercounted. The actual estimates would be 30 to 50% more. Yeah. When we study these homes, we found a common pattern. These homes are compact, densely packed, and often lack any ventilation. And the most important problem was the metal roof acted like a giant heat collector. After trying to address the different issues with different innovative solutions, we realized that the metal roofs absorb enormous amounts of solar radiation and radiates it during peak daytime, becoming an important problem to resolve. Indoor temperatures remain dangerously high, with the surface temperature of the bottom of the sheet reaching up to 60 degrees Celsius. To put that into perspective, 60 degrees is hot enough to cause third-degree burns in seconds. Now imagine living directly under that surface. The roof essentially becomes a radiator,
continuously pushing down heat into the home. Even when a fan is running, it often circulates hot air rather than providing comfort. So the roof became a primary focus. We studied existing solutions, cool roof panes, bubble insulation, and puff panels. While these solutions have benefits, they also present challenges. Cool roof panes don't perform with dust and still transfer heat through conduction and convection. Bubble insulation requires skilled installation and disrupts daily life during the retrofitting process. Puff panels are expensive and require significant structural support. It requires them to change the current roofing system as a whole. And so they become simply unaffordable for the families who need them the most. This led us to ask, can we design something that is affordable, easy to install, durable, effective, and suitable for informal housing?
Our answer is Coolchat, a modular rooftop retrofit system designed specifically for vulnerable urban homes. The idea is simple. Instead of allowing heat to directly enter the roof, we interrupt its journey. Coolchat uses three layers: a reflective layer, a ventilated air gap, and a non-ventilated air cavity. Together, these layers dramatically reduce the heat transfer into the home. No electricity, no water, no moving parts, just passive cooling through smart design. Firstly, the reflective layer reflects most of the solar radiation. The convection between the top layer and the tarpaulin below is prevented by the ventilated air gap. The last stage of conduction towards the roof is reduced by the non-ventilated air cavity, which has a conductivity of about 0.4 watt per meter Kelvin as compared to 66.8 watt per meter Kelvin of that of corrugated tin sheets. Developing the system required extensive experimentation. We explored a wide range of materials: aluminum sheets, flattened cans, PET bottles, bamboo, Tetra packs, coir, paper tubes, PVC pipes, tarpaulins. Each material was evaluated for their conductivity, reflectivity values, performance, cost, availability, ease of fabrication, and scalability. We tried a lot of permutations and combinations within the three layers and came up with various testing prototypes. We tested all of them with the metal roofing sheet and analyzed what materials worked better and what materials were easy to assemble as well. The following graph shows the results taken over various days, so the ambient temperature varies a little, but schematically one can see the temperature of the tin sheet that rises exponentially starting from the sunrise. The other lines depict which material helped us reduce this high temperature through the air gap. We started with a jute gunny bag with the infill of PET bottles, HDPE sack with double layered PET bottles and coir, bamboo pieces, repurposed cycle tubes. The data revealed that the surface temperature of the bottom of the metal sheet reduced drastically. In the specific case of the inflated cycle tube, the temperature drop was the highest, but it also delayed the cooling of the roof post the sunset, creating a thermal lag in both the ways. Also, the material posed a great issue with punctures and maintenance as well. After multiple iterations, we arrived at the final prototype. Using reclaimed paper tubes, tarpaulin, reflective aluminum coated HDPE, PVC spacers, and simple fastening systems. The system is 2 by 2 feet, so it is lightweight, modular, and designed to be assembled with minimal tools. This way, the product uses the market-ready products which are available in any city of the country, and they are widely used by people but in a loose manner, where the material joineries are haywire. Coolchat elevates these simple materials, brings them together in a heat-welded tarpaulin pillow. The first layer, which uses repurposed paper tubes, there are 11 paper tubes stacked with alternate paper tubes with reduced mass to reduce material redundancy, and then 3 through and through holes are made so that it can be tied with a nylon rope to make a flexible mat out of it. Next, some waste board pieces like PVC, MDF, jute board are taken on a 3 by 3 grid, which are glued to the tubes to provide a sturdy base for the rectangular PVC pipes that come in later. This mass is sandwiched between two tarpaulin sheets which are heat welded on all sides. That makes it water resistant, and seams are created so that the product can fold in one direction and accommodate a nylon rope in the other. The rope sits between the heat welded seams and continues through the modules. The ends can be used to tie the cool shut modules to the wall, hang some decoratives, or add some weight on it. In general, the hoop also helps get a grip on the modules and help move them when needed. The seam also accommodates metal snap buttons, which can quickly connect all adjacent modules. The seam also accommodates over the tarpaulin air pillow. The PVC pipes are glued over the wasteboard grid, and this creates a ventilated air gap between the tarpaulin and the aluminium coated SGP, which is the topmost reflective layer, and it has a reflectivity of 97%. Then Velcro is stitched on all four sides to connect all the top layers so that they are lapped horizontally and vertically. This gives you a water resistant roof, and still all the layers remain easily disassemblable and individually recyclable. Of course, innovation means little without evidence. So we tested the prototype under real outdoor conditions. Temperature sensors were placed on both a conventional metal roof and our prototype, and the results were encouraging. On different test days, Coolchat achieved surface temperature reductions of 7.7 degrees Celsius, 12.4 degrees Celsius, and up to 13.1 degrees Celsius. The roof temperature dropped from approximately 59 degrees Celsius to 45 degrees Celsius. Research shows that such reductions can translate to approximately 4 degrees of lower indoor temperatures. For someone living in a tin roofed home during peak summer, 4 degrees of difference can mean sleeping comfortably instead of struggling through the night, reduced heat stress, improved health, improved productivity, and a significantly better quality of life. We aim to change the street character from this to this, and adding to the thermal comfort, each house can customize the edge condition of their houses through choosing different color combinations of the tarpaulin and hang decorative pieces on them. This not only reduces the temperatures but also provides the sense of dignity and ownership to the user, which is also very important for them.
For this demographic, the solution to create impact, it must be affordable. We carefully analyzed materials, fabrication, logistics, operational costs, and our raw material costs right now are 75 rupees. And our estimated production cost per panel about 110 rupees. Our planned selling price right now begins at rupees 140 per panel, and each panel is 4 square feet. So the cost per square foot becomes 35 rupees, creating a sustainable yet accessible business model. As the years pass, the production cost will slowly go down and the selling price can be pushed up. We are still being conservative with our own cost production numbers as well as the demand numbers, which we are expecting to be higher than what we state. If we manage to achieve and function on those numbers, we are looking at a 18 lakh gross profit at the end of 3 years. And if we calculate and remove all our operating costs, about 7 lakhs, our net profit can be almost 10 lakhs in 3 years. And unlike air coolers, no electricity costs, no water consumption, minimal maintenance, and it works even during power cuts. No hidden payments, no electricity bills or issues for the next 3 to 4 years. Just a 5 to 6,000 rupee upfront cost. For low income households, this is a major advantage. Not only does our product deliver on being inexpensive, durable, and easy to install, but it also achieves passive cooling through no electricity, reuses waste, and also gives back the dignity of a regular temperature within the home, placing itself right in between its competitors, perfectly filling the gap. If we do manage to fill this gap and find ways of mass producing, this rather simple design with simple, readily available materials all across India put together cleanly, we would be changing lives. We also directly engaged with the users through our partnership with Saath NGO. We conducted testing with 10 volunteers, and the feedback was extremely valuable. Residents wanted strong cooling performance, durable materials, easy maintenance, modular and replaceable units, lower costs, and community validation before adoption. One important insight stood out. People just don't buy a product, they buy trust. This reinforced our strategy of working closely with NGOs, building pilot installations, and community demonstrations. Trust building becomes just as important as technological innovation. And our first attempt to gain the trust of this humongous target audience is our first pilot installation, which is already planned on Sultana Bain's roof. This pilot installation has also pushed us to improve our prototype over the last few weeks. People from other target groups, like poultry owners with animals dying due to heat, and struggling factory owners with workers affected by heat stroke, have also expressed interest in our product. Over the next year, we aim to validate performance in real homes, collect long term temperature and durability data, build partnerships with NGOs and CSR programs, refine manufacturing processes, and thereby bring down production costs. By year two, we would have secured our first commercial project, and by the end of year two, we would have hopefully delivered it. By year three, we would have started operating the startup on much better numbers. We are aware our goals might be slightly ambitious right now, but we want to push and achieve them. We will have to overcome issues like high prototyping costs, lack of long term data, limited capital, and trust barriers in our first year of incubation. After 3 years, we can also look at expanding into other hot climate regions like in Gujarat, as well as in states like Maharashtra and Rajasthan. We also envision multiple product variants that work for monsoon heavy climates, cold climates, etc., and decentralized manufacturing networks that create local employment opportunities.
The impact extends beyond cooling. It aligns with multiple SDGs, such as SDG 3, good health and well-being, SDG 11, sustainable cities and communities, SDG 12, responsible consumption and production, and SDG 13, climate actions. Additionally, every household that relies less on electrical cooling reduces energy consumption and carbon emissions. By lowering dependence on fans, coolers, and air conditioning, Cool Chats contributes directly to climate resilience. In other words, Cool Chat is not just a roof product, it is a climate adaptation solution. I'd like to end where we began. When temperatures rise, many of us can escape the heat, millions cannot. For families living under metal roofs, heat is just not merely discomfort. It affects sleep, health, productivity, and dignity. Cool Chat is our attempt to change that. A simple, affordable, scalable rooftop retrofit that can make vulnerable homes more cooler, safer, and more livable. Because everyone deserves a home that protects them from the elements, not one that amplifies them. Thank you, and we'd be happy to take your questions.
Thank you, team. That was well within time. Oh, yeah, absolutely, yes, please. Please use the mic as much as possible.
He won't ask any questions, don't worry. Go back and ask.
I was referring to the team.
Have you fixed it to a roof? An existing roof? How do you fix it to an existing roof so that it doesn't blow off?
Okay, so
The below we get the corrugations of the paper tubes as well, so it's meant to align with them, and it's because it's heavy enough to not fly away, and all of the modules are supposed to be stuck at the bottom and at the top, so we are not sticking it to the roof, which also makes it flexible if they want to get it removed during winters or whenever they want. So it doesn't require any skilled installations.
Moreover, we also have the nylon rope running, which can be used at decorative elements.
which you can use to tie from both
Tie
sides
it
of
down.
the-
Yeah.
Okay.
It can be used to add decorative elements weight, and that weight would additionally stop it from flying away more, as well as it can be given hooks at the end and it can be attached to the house and existing structure.
Okay. So
Can continue. This is just like two
This is
modules.
just two modules.
Question goes, so this is one mod. How do you connect the next module? This is 4 feet by 4 feet? No.
This is
Your modules are 4 feet by 4 feet?
It's 2 feet by 2 feet. Total
Four square feet.
Oh, okay.
So what we were thinking is we would have 6 such modules that go in one direction, and then you would actually connect modules in this direction. So they will, yeah. So in this direction, it will be one continuous. Think of it like a continuous sets of 6 pillows,
Yeah.
and then you will just join the next.
Join them or just place them next to each
No, you can join them. You can actually. So
this would be the second module.
correct. This is just an abstraction of that.
you can
You can.
additionally
Uh,
add this next layer.
the Velcro will be used to stick the top layer. So this is separated from the top layer with a ventilated air.
Sorry, I didn't get that. Come on.
So
That
can hold
one
this.
other.
So the connection for the bottom layer for the blue air cavity is separate from the top reflective sheet. So the next module, you will first connect the bottom with the snap buttons all the way, six pillows, and then the top layer would be you can
Would
remove
be
it with,
just
so you can
placed
just connect them
connected
separately.
from separate.
And we are also trying to do it across diagonally in a
We are also trying to do it diagonally, sort of in a shingling format, so that also helps with our waterproofing strategy for the roof. So it doesn't really seep in.
Because this would cover it when we finally clean.
So right now it's like this, but
When the next
you have
module
the
comes.
next module, it's gonna be like
But at the end, eventually you'll have some.
So eventually we can extend this a little bit to the end of the reflective sheet. So this is just a typical.
Yeah.
Then this needs to be
Like
at the end you'll have a different panel compared to the interiors.
the pan. Okay, it's not
Mm,
entirely a
no.
different panel, but yes, one component would be different.
What components will
A
have
little bit because then they're sure. If they're sure they don't need any more modules on that side, they can cut a small strip of that Velcro corner that you don't need this connection.
Yeah. These
So
are a
that
couple of issues that we're facing with our current pilot installation as well, because there are things which are already present on the roof. You have those dishes, etc. So how are we going to work our way around existing elements which might show up on the roof, and additionally take their help to sort of aid what we are also trying to do?
Bottom layer is sealed in a way, right? This one is completely. So how do you seal it? How is it sealed?
RF welding, heat welding. So it just bonds the two layers of
Two layers
tarpaulin together.
on the edges.
Yes, all 4 inches.
And how long will that last? Sealing? Because you're depending on that being sealed for a very long time for you to get the thermal conductivity.
We will have it sealed for at least 3 to 4 years till the tarpaulin starts degrading. Otherwise, the heat weld will stay.
How long do you tarpaulin? Okay.
Tarpaulin has a life cycle of 4 years without any maintenance, and post that you can maintain the tarpaulin as well.
But our aim was to, like, anyways, the tarpaulin won't be taking a lot of solar radiation because of the reflective layer.
So it
So
may also work longer, but we will have to test it for a period of 4 to 5 years to actually know.
This is a seal layer, whereas this is you're saying this is where the stack ventilation will sort of ventilate the cavity here. Is that what you're saying?
Yes.
Okay. And why can't you just make this also sealed? And why does this need to be ventilated?
Because so what happens is this is the reflective layer, so it does end up absorbing some amount of heat. So if we directly put a sealed air cavity under it, we will have convective heat passing through it, and sort of every degree counts.
Okay, so you
right
want
now.
to ventilate this part?
Yeah, just
So
to
that-
get rid of the connection
So
between
basically you're
the reflective
using
and
this
the
to shade this.
Yes.
Shade
And
this.
reflect off
most of it.
radiation that comes.
Yeah.
All right.
You do have around 7 more minutes of Q&A time left.
You have mentioned a conductivity of 0.07. Are you sure of those numbers?
So what we took was of the wall thickness of the paper tube that we have used and also the still air gap mass that we are getting. So right now we have just added those values and used it considering that the heat weld is properly sealed and then we are getting that amount of air cavity inside that pillow. So it's won't be exact because it's not a proper manufactured product with a proper conductivity value, but something we calculated with the layers. It has one paper tube thickness, air, and then another layer of paper tube. That's how we just brought a general number.
Okay. So I think you should do a better job than that because it will not be neither is paper homogeneous nor your air cavity homogeneous nor is it going to be perfectly sealed.
Yeah.
Right? Even the sealing that you've got might not be and it might deteriorate very quickly over time within one summer.
Okay.
The seal itself. Okay. So you're depending on that seal taking care of it being a completely sealed cavity. So what you do need to understand is that how quickly, how long will it last? How long will the seal last? I think it needs a little more R&D on that front. How long will that seal last? And is it possible to make that seal last longer than what you have envisaged it to be?
Okay.
Okay. So the 0.07 is only for the lower cavity?
Yeah.
Only for the lower,
Only for the lower.
only for the lower section. After that, it is just you're just elevating it, shading it,
Yeah.
and creating a reflective pattern. Okay. And what is the temperature differential you said you got? When you did that temperature differential from the, you said from the surface to the, what was the temperature differential?
The
Internal surface temperature?
the surface temperature difference which we got was 13.1 degrees.
Mm.
That's what the maximum that we got. We tested it over multiple days. So it was like 8 in some day, 12, 13. And we have just taken the surface temperature because ambient temperature would be very variable with the amount of openings, the size of the home.
No,
So
surface
yeah.
temperature is the right one to take. What was the external ambient and external surface temperature when?
Okay, so the days that we measured, it was around 42 degrees maximum temperature which was going on, and we have measured it around like 5 to 10 May around.
Okay.
Out of
So
5
it
to
was around
10,
42
yeah.
degrees externally, and the external surface temperature, did you measure the external surface versus internal?
The external surface temperature we haven't calculated, but we calculated the surface temperature of the tin roof which was kept and being tested aside from the prototype.
From the
So we saw what it could have been and what it is right now.
Okay. Okay, good. Well done.
Thank you.
Yeah, I think one more thing is we were also facing a lot of temperature variation when these were taken because monsoons had just hit Ahmedabad in the first week of June, which are the dates that we are giving right now. But we didn't want to claim any number based on one set of readings, so we have multiple.
Yeah.
Great job, team. Very good presentation, I must say, and loved your storytelling technique of how you'll work, explaining your idea. Also, a good point is that you all incorporated your prototype in your presentation. That's a good feedback for you all. I think one thing you'll need to think about, how are you going to productize this? Currently, it's just an idea level. So if you all are taking it ahead, I think you all must take it ahead. Think of productizing it. It's not there yet. I mean, how do you modularize it? Because when you're transporting it across regions, across cities, you'll need to think about this. Installation, modularization is important. The way it is right now, you might do it in Sultan Ben's home, but that's good for the study. To do a scale up, you'll have to think slightly differently. So just one piece of feedback for you all. But I think overall, I think you all have done a great job. Your value proposition is very clear. Who is this for, what it does. So great, congrats.
Thank you.
Yeah, agree with Kshitij over there. When you started the presentation, one feedback I had written was don't read from the script. And then I realized, okay, that's not really affecting your presentation. Good coordination also among all of you. I think you must have practiced it well and it shows here. What happens to this during monsoons?
So we have designed it, and like to it's anyways tarpaulin, which is a material they use during monsoons. It is a very water resistant material, and to not make it degrade, how we said, it is covered with another layer, and then again it's overlapped within all of them. So like considering most of the roof would be on a little bit of slope, using this shingle logic, most of the water should flow away. Whatever comes inside also can go, and then again it's a ventilated air gap, so it can dry up again. So if someone wants to,
Won't there be water accumulation because your top surface, the PVC openings, they are not uniform.
Yeah.
You have them, in isolated places. So it's very ripe for water to, accumulate in the unevenness in the surface that forms there. And won't there have other consequences? Accumulated water can lead to a lot of breeding of
mosquitoes.
and
Yeah. We can try this again in monsoon and then see how we can make it more under tension to make it more flat.
Yeah, but I think um, by the in the time frames with which we were sort of working right now, our main focus was to bring down the heat and those temperature costs. So we haven't really looked into the waterproofing as much. We know it's a very important aspect of our product, and we are resolving that as we go through our first pilot, their expectations and small things like the shingling and all are there. But yeah, we are aware we may have to get into waterproofing a little bit more.
And the paper cylinders that you have used, are those readily available or are those custom parts made specifically for this product?
No, they are very readily available. We are
Which industry uses those?
architecture students, print shops. All print shops across the country are using this.
Very soon you're going to run into a problem, right? After 200 units or 500 units, you don't know what to do. So I think that's where he's coming from. Because when you need to scale up for mass production, I don't think you can rely on architecture students.
No, there are
For that,
other
you have to
products.
make sure architecture students are getting into colleges and that number is increasing.
But there are other industries also which are using these kind of paper tubes, which are your aluminium rolls, your tissue paper rolls, etc. as well. And these are in production. So if we ever sort of run out of sourcing this thing as a waste material, we have the option to reaching out to other industries and picking it up directly from there.
Okay, I got the signal. Thank
If you
you.
have one question, I'll give you one last question from all three of you.
I do have a question. So how did you arrive at your selling price of 140?
For now, we just wanted to start with a acceptable price for Sultana Bin. What she said is about 5 to 6,000 rupees seems acceptable to her. The panel calculation for her right now is we need 28 panels. And if we multiply and see the cost, she would have to end up paying about 4,000 rupees, which works for her. So for now, we have started from there and we will slowly build it up. And once we have the trust in the product and people are willing to put in, we can go up to about 6,000, 7,000 rupees.
This is not sustainable. This at this price point, you won't be able to scale. You won't make any margins out of your product.
Right. For now, we are definitely not claiming that we are an extremely profitable business. But
Not at all profitable.
no, we are thinking. But but 3 years down the line, we will, when we have put in the capital costs into manufacturing this and setting up a process of producing n number of panels per day when our demand is that much, I think, and the sheer demand is the scale of the target audience is something which is massive. It's an extremely untapped into market if we think about it. There is a system of making money and then making products for the people who have the money to spend on those products, but we don't really have an industry working towards making products for this demographic. But it is not that they don't need design products, they still do need design products. So this will be sort of a gateway. We will tap into that market, and that is, we are right now the top 1 to 10% of the country sitting in this room. The rest of the 90 is out there waiting to tap into such products. So hopefully the demand will take care of that.
Okay, thank you.
One last sort of advice, also no question, is that you need to look at maybe something other than paper, because it will at some point soak up water, start having fungus, degrading very fast once that happens. So you might have to look at the other alternative to that paper roll that you have to make it last longer.
Right. Thank you, Jude.
We just have one last thing to say.
30 seconds.
10 seconds.
Fine.
अगर आप गर्मी से हो गए हैं लत-पत तो लगाइए कूल छत.
Thank you. Thanks for the presentation. Yeah, you can take your seats. Yeah. Okay, so that was the last presentation in the RCR division. So our esteemed jury panel have shown immense dedication for assessing all your entries, and I want to thank them. Thank you, jury members, for your thoughtful assessment and comments. And I also want to congratulate all the finalists in this room. So as a jury coordinator for this division, I have had the opportunity to see all the teams submit their deliverables, and they have done some incredible work. Okay, getting here in 7 months' time, along with your, academics, is a great achievement. A big hand to all of you. So jury members, thank you for your time. Thank you for your feedback. Thank you for all the finalist students for your participation. We'll break for tea in a while, and jury members will meet this evening to decide the winners and the runner-up. They'll have deliberations, and they'll do the final decisions. We have an exhibit that's called the Climate Smart Innovation Exhibition, where you get to see innovative building products from the industry that address climate change. So this exhibition is open, and if you proceed to the multiplex zone, you can see the exhibition there. Being participants in the product division, I highly recommend that please go and have a look at these products and the companies who are exhibiting them there. And for the people who are online, we're going to end the stream now. Please stay tuned on our channel at 6 p.m. Watch the 10 Climate Smart Innovation exhibitors pitch their products in a bid to win the Climate Smart Innovation Award. So until then, have a great evening.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. The world is so hot.